Look at this image. It is a photograph of Earth taken from a distance of over 3.9 billion miles. Our world is not a majestic blue marble, not a swirling sphere of clouds and oceans. It is a single, pale blue pixel, suspended in a sunbeam. This is the pale blue dot, and in its profound simplicity, it captures everything. It is a whisper of existence against the vast, silent darkness. This image, like so many others from the frontier of space, is more than just a picture. It is visual poetry. It speaks a language that bypasses our intellect and touches something deeper, something primal within us. It evokes a sense of awe, of humility, and of a mystery so vast it is almost impossible to comprehend. But what if this poetry is not merely for inspiration? What if it is actually a language, a fundamental code for deciphering the universe's greatest secrets? We are living in an era unlike any other in human history. Our eyes have been gifted with an extraordinary new vision. Telescopes orbiting high above our atmosphere act as time machines, capturing light that has traveled for billions of years, allowing us to literally look back into the past. On the surface of distant worlds, robotic rovers serve as our artists, their lenses translating alien landscapes into breathtaking panoramas that tell stories of ancient rivers and violent cosmic winds. These are not cold, clinical datasets. They are vibrant, dynamic portraits. They bridge the immense gap between the abstract numbers of physics and the raw, human emotion of wonder. They allow us to witness the birth of stars in swirling nebulae, to ponder the invisible grip of dark matter by seeing its ghostly gravitational hand distorting galaxies, and to stand virtually on the dusty plains of Mars. This is the power of cosmic imagery. It transforms the unknown into the observable and the mysterious into the tangible. In this video, we will embark on a journey through this visual poetry of space. We will explore how these incredible images are created, from the first-hand sketched drawings of astronomers to the complex, multi-wavelength composites built from data collected by our most advanced observatories. We will learn to read the stories they tell, to understand the narratives of cosmic evolution, stellar life and death, and the very structure of reality itself, all encoded in light and shadow. We will see how a single, seemingly empty patch of sky can reveal thousands of galaxies, and how a faint radio wave shadow can confirm the existence of a supermassive black hole. Prepare to see the cosmos not as a random scattering of lights, but as a grand visual narrative, a storybook written in the language of physics, waiting for us to learn how to read it. And to understand how we learn this language, we must begin at the very beginning with the first tools of this cosmic art form. Our story begins not with a digital sensor, but with a quill pen and a sheet of paper. In the year 1609, Galileo Galilei first turned his small, primitive telescope towards the moon. What he saw shattered an ancient belief. The moon was not a perfect, smooth celestial sphere as philosophers had long claimed. It was a world. Its surface was rugged, marked by mountains, and most strikingly, pockmarked with circular craters. With painstaking detail, Galileo began to sketch what he observed. These were not artistic impressions, they were the first data visualizations in astronomy. His drawings of the lunar terminator, the line dividing light from shadow, used chiaroscuro to reveal the three-dimensional nature of the lunar landscape. This was the moment humanity began its visual conversation with the cosmos. We were no longer just looking up in wonder, we were starting to document, to record, and to understand. Each stroke of Galileo's pen was a question, and the moon, for the first time, was beginning to answer. For centuries after Galileo, the human eye and hand remained the primary tools for cosmic observation. Astronomers would peer through ever larger telescopes and draw what they saw, but the eye is subjective and limited. It cannot collect light over time to see fainter objects. This all changed in the 19th century with the advent of photography. Suddenly, astronomers could attach a photographic plate to their telescope and take a long exposure. Instead of a momentary glimpse, the plate would accumulate light for minutes or even hours, revealing celestial objects far too faint for any human eye to perceive. This was a revolution in objectivity. The first photograph of the moon was taken in 1840, but the real breakthrough came with images of nebulae. What had appeared as faint, fuzzy smudges through the eyepiece were revealed on photographic plates as intricate structures with complex shapes. The Andromeda Galaxy, for instance, was captured in all its sprawling glory, its spiral arms hinting at a dynamic universe. Photography turned astronomy from a descriptive science into a forensic one. The sky was no longer a static tapestry. It was a recording medium, and light was the message. The next great leap required us to leave our own planet behind. For all their power, Earth-based telescopes have a fundamental limitation. They must peer through our atmosphere. The air is never still. It ripples and churns, causing the light from stars to twinkle. While romantic to the naked eye, this twinkling is a nightmare for clarity, blurring the fine details of distant galaxies and nebulae. The solution was to place a telescope above it all. In 1990, the Hubble Space Telescope was launched into orbit, and after an initial flaw was corrected, it opened a new window on the universe. Free from the distorting effects of the atmosphere, Hubble delivered images of a crispness and depth that were unimaginable from the ground. Its iconic pictures, like the pillars of creation in the Eagle Nebula, did more than just advance science. They became cultural touchstones. They were downloaded as desktop wallpapers, printed on posters, and featured in news magazines around the world. Hubble made the cosmos accessible and vividly real for an entire generation, proving that the beauty of the universe could be a powerful force for inspiration and education. But Hubble was just one part of a broader expansion of our vision. Astronomers realized that the universe speaks in more than just the narrow band of light visible to our eyes. It broadcasts in a full spectrum of energy, from long wavelength radio waves to incredibly short and energetic gamma rays. Each type of light reveals a different cosmic process. To see this invisible light, we needed new tools. Radio telescopes, like the Very Large Array with its giant dish antennas, began mapping the cold hydrogen gas between stars and the violent jets shooting from galactic cores. X-ray telescopes like Chandra focused on the high-energy universe, imaging the superheated plasma around black holes and the remnants of exploded stars. To make sense of this data, scientists developed the technique of false color, assigning visible colors like red, green, and blue to these invisible wavelengths. This is not about making things up, it is about translation. It allows our brains to intuitively grasp the structure and composition of objects we could never otherwise perceive. A single image of a galaxy cluster might combine optical light from Hubble, X-ray data from Chandra, and infrared light from Spitzer, creating a multi-layered portrait that tells a complete story of gravity, gas, and dark matter. This entire historical progression, from Galileo's sketches to Webb's infrared vistas, reveals a profound truth. Our understanding of the cosmos is not separate from the images we create of it. They are fundamentally linked. Every time we expand our visual palette, every time we improve the fidelity of our cosmic portraits, we unlock new mysteries and challenge old assumptions. A clearer image is not just a prettier picture, it is a deeper question. It is the difference between seeing a faint smudge and recognizing a distant galaxy, between observing a point of light and resolving a planetary system in formation. The history of cosmic imaging is the history of our growing conversation with the universe. Each technological breakthrough is a new phrase in that dialogue, allowing the cosmos to reveal itself in ever more stunning and complex ways. But if our history of looking up has taught us one thing, it is that our eyes are incredibly limited receivers. The rainbow we see is just a tiny sliver of a vast electromagnetic spectrum, a cosmic symphony playing in wavelengths our biology simply cannot perceive. The truth is, most of the universe's drama, its most violent births and deaths, its grandest structures and its faintest whispers, are happening in a theater of invisible light. To truly see the cosmos, we must learn to paint with this invisible light, using our telescopes as brushes to reveal a universe far more dynamic and colorful than we ever imagined. Consider the high-energy universe, a realm of extreme violence and power. When a star explodes in a supernova, or when matter is ripped apart and superheated as it spirals into a black hole, it doesn't just emit visible light, it screams in X-rays. These are photons carrying immense energy, born from temperatures of millions of degrees. To capture this fury, we have observatories like the Chandra X-ray Observatory. Orbiting high above Earth, Chandra acts as a coroner for cosmic catastrophes. Its images show us the aftermath of stellar explosions not as delicate wisps, but as vast, expanding bubbles of multimillion-degree gas. They reveal the intense, pinpoint brilliance of material orbiting a black hole just before it crosses the point of no return. A Chandra image of a galaxy cluster, for instance, doesn't just show the serene glow of billions of stars. It unveils a colossal cloud of superheated plasma that fills the space between galaxies, a visible testament to the gravitational power of the cluster itself. This is the universe in a palette of fury, a visual language of pure energy. Now travel to the opposite end of the spectrum, to the long, gentle waves of infrared light. If X-rays show us the universe's death throes, infrared light reveals its birthplaces. Our galaxy is filled with enormous, dark clouds of gas and dust, the raw material for new stars. To our eyes, these clouds are impenetrable curtains, blocking the light of the stellar nurseries within. But infrared light has a special property. Its longer wavelengths can slip between the dust grains like a fog light piercing a mist. This is the specialty of telescopes like the now-retired Spitzer Space Telescope and its colossal successor, the James Webb Space Telescope. By observing in infrared, they can peer directly into the heart of these cosmic nurseries. What appears as a dark blotch in a visible light image is transformed into a vibrant, cavernous structure teeming with infant stars. We can see the glowing dust sculpted by stellar winds and the faint heat signatures of protostars still cocooned in their gaseous envelopes. This is a universe of quiet creation, hidden from our ordinary sight but revealed in all its delicate glory by our infrared vision. So how do we translate these invisible signals into the images that inspire us? The answer lies in a process often misunderstood: false color. When a telescope like Chandra or Webb takes a picture, it doesn't capture a ready-made color photograph. It collects data counting photons of specific, invisible wavelengths. Scientists then assign a visible color to each of these data sets. For a Chandra image of a supernova remnant, they might map the highest energy X-rays to blue, medium energy to green, and lower energy to red. For a Webb image of a nebula, they might assign different infrared wavelengths to specific colors to highlight the presence of different molecules like hydrogen or carbon. This is not an artistic lie, it is a scientific translation. It is akin to a doctor assigning colors to different types of tissue in an MRI scan to make the anatomy clearer. The resulting image is both intuitively understandable and rigorously scientific. It is a map, a guide that allows our brains to comprehend the complex physical processes, the temperatures, densities, and chemical compositions at play in a distant cosmic object. This act of translation is perhaps the most crucial step in modern astronomy. It transforms columns of numbers and graphs of intensity into a visual story that we can explore and understand. A single multi-wavelength image of a galaxy becomes a biography. The visible light shows us where the adult stars are shining. The infrared reveals the hidden nurseries where new stars are being born. The X-rays pinpoint the locations of stellar remnants, black holes, and neutron stars, the graves of previous generations. Without this technique, much of the universe's narrative would remain locked away in spreadsheets and databases, inaccessible to our pattern-seeking minds. By painting with invisible light, we don't just make pretty pictures. We create a comprehensive visual language that allows us to read the life cycle of galaxies, from their turbulent beginnings to their energetic deaths, across the full breadth of the cosmic spectrum. This ability to see the whole story sets the stage for one of the most profound visual revelations of all, a single image that forever changed our sense of scale. By the mid-1990s, the Hubble Space Telescope had already dazzled the world with its portraits of nearby planets and brilliant nebulae. Yet, a fundamental question about the universe at its largest scales remained frustratingly unanswered. When we look between the bright, nearby stars, what lies in the apparent emptiness? Some cosmologists theorized that if you stared long and deep enough into a truly dark patch of sky, you would find a universe filled with faint, distant galaxies. Others were not so sure. To settle this, a team of astronomers made a radical and risky proposal. They wanted to commandeer Hubble for 10 entire days, an enormous allocation of its precious time, and point it at a patch of sky near the Big Dipper that was chosen specifically because it was nothing. It was devoid of bright stars, distant planets, or known galaxies. It was, for all intents and purposes, a blank canvas. This was a tremendous gamble. What if they pointed the most expensive telescope ever built at nothing, and after 10 days they found precisely that, nothing? The telescope began its long exposure, collecting photons one by one, over what would ultimately amount to 150 orbits of the Earth. As the data trickled in, the team assembled the first tentative images. At first, there were just a few faint smudges, then more appeared, and then more. By the time the full dataset was processed, the result was breathtaking. The blank canvas was not blank at all. It was crammed with a staggering 3,000 galaxies of every conceivable shape and size. Each of those tiny, faint smudges was not a star, but an entire island universe, home to hundreds of billions of stars itself. The scale of this revelation is almost impossible to grasp. The area of sky Hubble stared at is astonishingly small. Imagine holding a grain of sand at arm's length. The patch of sky it would cover is the exact size of the Hubble Deep Field. Within that pinprick of darkness, Hubble found a universe teeming with life in a cosmic sense. But the deep field was more than just a census. It was a core sample of the universe, a geological dig through time itself. Because light takes time to travel, looking out into space is equivalent to looking back in time. The galaxies in the deep field are not just far away, they are seen at different epochs in cosmic history. Some of the faintest, reddest smudges are infant galaxies, seen as they were when the universe was only a fraction of its current age. We see them not as the majestic spirals and ellipticals of today, but as smaller, irregular blobs caught in the act of formation. This single image, therefore, is not a static portrait. It is a family album spanning billions of years, showing us galaxies in their youth, their adolescence, and their maturity, all within a single frame. The statistical impact of this image was immediate and profound. If this one random, minuscule patch of sky contains 3,000 galaxies, then the entire observable universe must contain a number so vast it defies everyday comprehension. Astronomers extrapolated that there are likely 200 billion galaxies, a number that has since been revised even higher. This single visual observation transformed our quantitative understanding of the cosmos. It also raised profound new mysteries. The sheer number of galaxies and their seemingly uniform distribution across the sky posed new challenges for theories of how structure forms in the universe. Why are they spread out this way? How did they evolve so quickly? The deep field answered one monumental question only to open a dozen new and even more fascinating ones. Perhaps the most enduring legacy of the Hubble Deep Field, however, is the profound sense of perspective it imposes. It is an image of overwhelming humility. It visually demonstrates that our entire Milky Way galaxy, with its hundreds of billions of stars and our own pale blue dot, is just one of an unimaginable multitude. There is no center stage in this cosmic view. We are residents of a single, ordinary galaxy, lost in a crowd of hundreds of billions. The poetry of this image lies in its quiet contradiction. It is visually simple, a dark background scattered with faint points of light, yet the story it tells is one of the most complex and grand narratives science has ever uncovered. It set a new standard for cosmic exploration, proving that sometimes the biggest discoveries are hidden not in the bright and obvious places, but in the deepest, darkest voids, waiting for us to look long enough and deep enough to see them. This hunger to look even deeper, to peer back to the very dawn of time, would require a new telescope with a revolutionary vision. The Hubble Deep Field gave us a profound sense of our place in a crowded cosmos, but it also ignited an even deeper hunger. What about the very first galaxies? What did the universe's opening chapter look like? To answer that, we needed a telescope that could act as a true time machine, one designed not just to see far, but to see back. That telescope is the James Webb Space Telescope, Hubble's revolutionary successor, and its mission is to capture the universe's first light. This quest to see the dawn of time is not a matter of building a bigger version of Hubble. It requires a fundamentally different kind of eye. The expansion of the universe itself presents the central challenge. The light from those first stars and galaxies has been traveling for over 13 billion years to reach us. During that unimaginable journey, the very fabric of space has stretched, and this stretching has a direct effect on the light waves within it. They get pulled to longer, redder wavelengths. This phenomenon, called cosmological redshift, means that the brilliant ultraviolet light emitted by the first hot, young stars has been shifted all the way into the infrared part of the spectrum by the time it arrives at our doorstep. It is light that has literally run out of energy, fading into a warmth that our eyes cannot see. Hubble, optimized for visible and ultraviolet light, is mostly blind to this ancient signal. James Webb, however, was specifically engineered to see it. Its primary mission is to be an infrared telescope, a heat-sensitive eye tuned to the faint, stretched whispers of the cosmic dawn. To achieve this, Webb's design is radically different. Its most striking feature is a tennis court-sized sunshield, a 5-layered silver kite that perpetually positions itself between the telescope and the Sun, Earth, and Moon. This shield is essential because it allows Webb's instruments to cool down to staggering -400 degrees Fahrenheit. At that temperature, the telescope itself stops glowing with infrared heat. preventing it from blinding itself to the faint infrared glow of the distant universe. Then there is its mirror. While Hubble's mirror is a single piece of glass, Webb's is a masterpiece of origami in space, 18 hexagonal segments of gold-coated beryllium that unfolded with painstaking precision after launch. This golden mirror, over 6 times larger than Hubble's light-collecting area, acts like a colossal bucket, gathering every precious photon of infrared light from the edge of time. The world got its first taste of Webb's power in July of 2022, when its initial images were released. Among them was a sight that immediately captured the public's imagination: the cosmic cliffs of the Carina Nebula. While Hubble had given us a beautiful view of this stellar nursery, Webb's infrared vision tore away the veil. What appeared as an opaque, dusty mountain in visible light was revealed to be a cavernous, ethereal landscape. Webb's view showed the nebula's gas and dust as semi-transparent, glowing with the light of hundreds of previously hidden newborn stars. We could see the fierce stellar winds from these massive infant stars actively sculpting the nebula, carving out bubbles and pillars in a dramatic cycle of creation and destruction. This image was not of the ancient universe, but it was a stunning declaration of Webb's ability to see through cosmic dust and reveal the processes of star formation with a clarity we had never before possessed. But the real magic of Webb goes far beyond creating beautiful postcards. Its most profound work is in spectroscopy, the science of splitting light into its constituent colors to create a fingerprint. Every element in the universe leaves a unique barcode of dark or bright lines on this spectrum. Webb's instruments can take the spectrum of a single, incredibly faint galaxy located billions of light-years away. By analyzing this fingerprint, scientists can determine the galaxy's chemical composition, its distance, its temperature, and even the speed at which it is forming stars. This raw data is then translated into the stunning images we see. The process is a form of scientific storytelling. For instance, to create an image of a distant galaxy, astronomers might assign specific infrared wavelengths that correspond to oxygen, hydrogen, and sulfur gas to the colors red, green, and blue. The resulting picture is not a literal snapshot of what we would see, but a chemically rich map. It tells us where different elements are located, revealing the structure and physical conditions within that galaxy. It turns abstract data into a visually intuitive story of cosmic evolution. This capability is what allows Webb to build visual timelines of the universe. By observing galaxies at different distances, and therefore different look-back times, Webb is assembling a photo album of galactic growth. We can now compare a galaxy as it was just a few 100 million years after the Big Bang to one that is a few billion years old, and to the majestic spirals we see today. We are starting to see how the first, small, chaotic clumps of stars merged and grew, how their first generations of stars, which contained almost no heavy elements, seeded the cosmos with the building blocks for planets and life. With each new observation, Webb is confronting one of cosmology's greatest mysteries. How did a smooth, hot, primordial soup of particles evolve into the intricate cosmic web of galaxies, clusters, and voids we see today? It is providing the visual evidence, the missing pages from the universe's childhood, that will help us write the story of how everything we know came to be. While we have been gazing across the cosmos at galaxies and nebulae, another, more intimate form of visual poetry has been unfolding much closer to home, on the rusty surface of our planetary neighbor, Mars. Through the electronic eyes of robotic geologists like Curiosity and Perseverance, the red planet has been transformed from a distant, blurry orb into a tangible, explorable world. These rovers provide a perspective we can instinctively understand, a human-scale view of an alien landscape. They have turned Mars into a place that feels at once strangely familiar and profoundly otherworldly, a duality that lies at the heart of its visual allure. Consider a simple sunset. On Earth, we are accustomed to a sky that blazes with oranges and reds as the sun dips below the horizon. But on Mars, the sunset tells a different story. The Perseverance rover has captured this daily event, and the image is quietly astonishing. The sun is a small, sharp disk, its light diffused by the thin Martian atmosphere. And the sky around it is not a warm glow, but a cool, serene blue. This reversed palette is a direct result of the Martian environment. The fine, iron-rich dust that gives the planet its red color is perfectly sized to scatter blue light across the sky, much like tiny molecules in Earth's atmosphere do, but with the colors inverted. This single, serene image is a masterpiece of planetary science in visual form. It requires no complex explanation to feel its impact. It speaks a universal language of day's end, while its peculiar hue whispers the specific, dusty truth of an alien world. This visual storytelling extends from the sky down to the very ground the rovers tread. The panoramas beamed back from Gale Crater, where Curiosity has been roaming for over a decade, are not merely beautiful landscapes, they are open history books. The rover's cameras have captured towering Mount Sharp, revealing its flanks as a series of distinct sedimentary layers. Each layer is a chapter deposited over eons by wind and, crucially, by water. You can see with your own eyes the evidence of ancient streams and lakes that once filled this crater. The rocks themselves are not random rubble. They are often finely layered, like pages pressed together, telling a story of cyclical flooding and drying. More recently, the Perseverance rover landed within Jezero Crater, a site chosen specifically for its dramatic visual promise of a watery past. From the surface, the rover's cameras have confirmed what orbital images suggested: the unmistakable, fan-shaped topography of an ancient river delta. Where a river once fanned out into a lake billions of years ago, depositing sediments that could have trapped and preserved signs of microbial life, we now have a robotic field geologist examining the rocks. These images make the abstract concept of a wet Mars visceral and immediate. We are not just being told about an ancient lake, we are being shown its dried-up shoreline, its riverbeds, and its deltas. Every single image from these missions, from a sweeping horizon shot to an extreme close-up of a rock target under the rover's microscope, serves a dual purpose. They are both postcards from another world, designed to inspire awe and connection here on Earth, and they are rigorous scientific data. A curious rock formation is not just a subject for a photograph, it is a hypothesis. The arrangement of sand dunes speaks to the prevailing winds. The texture of a pebble can reveal whether it was tumbled in a river or shaped by desert winds. The rovers are, in effect, translating the complex language of geology into a visual narrative we can all follow. They are our proxies, our eyes and hands on a world 100 million miles away, turning pixels and data into a profound sense of place. This human-scale exploration makes the grand mystery of Mars history intensely personal and compelling. It invites us to stand, virtually, on that dusty plain and look out at the hills, wondering what this world was like when water flowed and the air was thick. It transforms the scientific quest for past life from a theoretical exercise into a tangible hunt, one where the next rock, just over the next ridge, might hold the clue. By bringing Mars so vividly into our living rooms, these robotic artists have done more than just advance science. They have ignited our collective imagination, making the question of whether we are alone in the universe feel tantalizingly close to being answered and turning our gaze firmly toward the next logical step, sending human eyes to see these landscapes for themselves. While our rovers give us a grounded perspective on planetary landscapes, if we turn our gaze back towards home, we find a celestial drama of an entirely different scale playing out right above our heads. The Sun, that familiar orb that defines our days, is far from the serene, unchanging disk it appears to be. Through the advanced eyes of satellites like the Solar Dynamics Observatory, or SDO, our star is revealed as a seething, dynamic sphere of incandescent plasma, performing a continuous and violent ballet of forces so immense they defy comprehension. This is not a gentle light in the sky. It is a continuous cosmic storm, and its imagery tells a story of creation and destruction happening in real time. Perhaps the most visually stunning features of this solar drama are solar prominences. These are vast, elegant arcs of superheated gas or plasma that leap from the Sun's surface and travel hundreds of thousands of miles into space. They are not random eruptions, they are sculpted. The plasma, made up of charged particles, is guided along the invisible pathways of the Sun's powerful magnetic field, like iron filings aligning around a magnet. These loops can remain stable for days or even weeks, tracing beautiful, fiery curves against the blackness of space, but their beauty belies their power. A single prominence can contain more material than all the rivers on Earth combined, a testament to the sheer scale of solar activity. When these structures become unstable, they can collapse back onto the Sun's surface or erupt outward, becoming part of an even more powerful event. Observing these prominences in different wavelengths of light allows scientists to map the Sun's complex magnetic skeleton, turning a beautiful visual phenomenon into a crucial diagnostic tool for understanding our star's inner workings. If prominences are the Sun's elegant arcs, then coronal mass ejections are its mighty cannon blasts. These are among the most powerful eruptions in our solar system. Imagine a billion-ton cloud of magnetized plasma hurled away from the Sun at speeds of several million miles per hour. Satellites like SDO and the SOHO Observatory provide us with a ringside seat to these colossal events. Using special instruments called coronagraphs, which block out the Sun's brilliant face, they capture the moment a CME bursts free, expanding outwards like a cosmic shockwave. Tracking these billion-ton clouds is not just an academic exercise, it is a critical part of space weather forecasting. When a CME is directed towards Earth, its arrival 1 to 3 days later can trigger spectacular auroras, but it can also wreak havoc on our technology. The intense magnetic fields carried by the ejection can induce powerful currents in our power grids, potentially causing widespread blackouts. They can disrupt satellite communications, knock out GPS systems, and pose a radiation hazard to astronauts. The visual data from these observatories gives us a vital heads-up, allowing operators to take protective measures and safeguard the technological infrastructure that modern society depends on. Zooming in closer to the Sun's visible surface, known as the photosphere, reveals a texture that is surprisingly familiar. High-resolution images show a surface that is not smooth but granulated, like a pot of boiling water or the surface of oatmeal. Each of these granules is a cell of rising hot plasma, brighter at its center, which spreads out, cools, and then sinks back down into the darkness at its edges. This is the visual signature of convection in action, the same process that heats a room with a radiator. But on the Sun, the scale is staggering. A single granule is typically about the size of Texas, and the entire surface is a constantly shifting mosaic of millions of them, with each cell lasting only about 10 minutes before being replaced. This churning cellular pattern is the most direct visual evidence of the tremendous heat and energy generated in the Sun's core, slowly making its way to the surface to be radiated away as light and heat. Amidst this boiling sea, darker patches often appear, sunspots. These are not truly dark, they are just slightly cooler areas on the sun's intensely hot surface, appearing dark only by contrast. They are created by intense concentrations of magnetic field lines that erupt through the photosphere. These powerful magnetic fields inhibit the convection process, preventing heat from rising efficiently to the surface, which cools the area down. Sunspots are rarely solitary. They often appear in groups, and their number, size, and location follow a well-documented 11-year cycle. By visually tracking sunspots for centuries, astronomers have mapped this cycle of solar activity from a quiet period known as solar minimum, with few or no spots, to a frenetic solar maximum, when the sun's face can be dotted with many large groups. This long-term visual record is our primary key to understanding the sun's internal magnetic dynamo, the complex engine deep within our star that generates its powerful and ever-changing magnetic field. This constant, multi-wavelength visual monitoring by a fleet of solar observatories has fundamentally transformed our relationship with the sun. It is no longer a distant, static lamp in the sky. Through imagery, we see it as a living, breathing entity with a complex anatomy and a volatile personality. The mysteries of how its magnetic dynamo operates, or why its outer atmosphere, the corona, is millions of degrees hotter than its surface, a puzzle known as the coronal heating problem, are no longer abstract theoretical concepts. They are visual problems. Scientists can watch energy transfer, magnetic fields tangle and reconnect, and plasma heat up in real time. The imagery provides the clues, the moving pieces in a grand puzzle, making the most fundamental processes of stellar physics accessible and tangible. The sun's fiery ballet, captured in stunning detail, reminds us that we orbit a star of immense power and complexity, one whose daily performance directly shapes the environment of our entire solar system. Leaving the sun's turbulent surface behind, we venture outward to a realm where weather is not measured in days or years, but in centuries, and where the very atmosphere becomes a canvas for physics on a truly monumental scale. The gas giants Jupiter and Saturn present a form of visual poetry that is both serene and violently dynamic, a study in contrasts that reveals the fundamental forces shaping worlds without a solid surface. Jupiter, the solar system's titan, is a masterpiece of atmospheric chaos. Its face is not a single color but a tapestry of swirling bands, alternating stripes of creamy whites, deep oranges, and subtle browns. These are not mere decorations, they are the visible manifestation of a planetary-scale engine. The light-colored bands, called zones, are where gas is rising from the planet's scorching interior. The darker bands, known as belts, are where this gas cools and sinks back down. Caught between these colossal rising and falling currents, the atmosphere is sheared into these incredibly stable jet streams, some blowing at over 300 miles per hour in opposite directions. The sheer scale is humbling. A single one of these bands is wider than our entire planet, and the entire system is a self-sustaining weather machine, powered by the internal heat left over from Jupiter's formation and the relentless spin of the planet, which completes a rotation in just under 10 hours. To gaze upon Jupiter is to witness the raw power of fluid dynamics painted across a canvas 86,000 miles wide. And at the heart of this swirling majesty lies its most iconic feature, a storm so vast it has become a planetary landmark, the Great Red Spot. This is not a temporary hurricane. It is an anticyclonic maelstrom that has been churning for at least 350 years and possibly much longer. Its most staggering characteristic is its size. While it has been shrinking over the past century, the Great Red Spot is still so large that our entire planet Earth could easily fit inside its swirling winds. Imagine a storm that could swallow your world whole, and then imagine that storm persisting through centuries of human history. Its distinct reddish hue, likely caused by complex chemical compounds like ammonium hydrosulfide being brought up from deeper layers and broken apart by solar ultraviolet light, adds to its enigmatic presence. But the spot is more than just a static wonder. It is a vital long-term weather station. By observing its changes in size, color, and drift rate over decades, planetary scientists gain invaluable insight into the stability of Jupiter's atmosphere and the complex energy balance that fuels such an enduring tempest. It is a living laboratory for hyperstorm physics, a visual record of meteorology operating under conditions we can never replicate on Earth. In stark contrast to Jupiter's turbulent beauty, Saturn presents an aura of almost serene, banded elegance. Its palette is softer, a muted harmony of golds, tans, and yellows, with cloud features that appear more diffuse and less violently contorted than its larger sibling. This calmer appearance is partly due to a deeper layer of hazy mist in Saturn's upper atmosphere, which smooths out the finer details. But do not be fooled by this placid facade. Saturn's weather is just as fierce, with wind speeds at its equator exceeding 1,000 miles per hour, far faster than any hurricane on Earth. Yet the most stunning visual mystery on Saturn is found not at its equator, but at its north pole. There, the Cassini spacecraft revealed something that seems to defy natural formation, a perfect giant hexagon. This six-sided jet stream, each side longer than the diameter of Earth, encircles the pole with geometric precision. It is a persistent wave, a standing pattern in the atmosphere that has been observed for decades. How such a perfect polygon can form and remain stable in a turbulent gaseous environment is an active area of research, a captivating puzzle where the laws of fluid dynamics produce an apparently artificial-looking structure. It is a breathtaking reminder that nature's artistry often surpasses our own imagination. The legacy of the Cassini mission, which spent 13 years orbiting Saturn, fundamentally transformed these distant points of light into a complex planetary system we can explore in intimate detail. Nowhere is this more evident than in its breathtaking studies of Saturn's rings. From Earth, the rings appear as a single, solid disk, but through Cassini's eyes, they were revealed as a vast, intricate ballet of countless icy particles, ranging in size from tiny grains to mountains. The images show an astonishing level of structure: braided rings, spiraling density waves, and sharp gaps cleared out by the gravitational influence of tiny shepherd moons. The rings are not a static sculpture, they are a dynamic, evolving system. Cassini captured sunlight scattering through the rings, revealing their thinness in some places, no thicker than a 3-story building, despite stretching over 170,000 miles across. The mission's grand finale, a series of daring dives between the planet and its innermost ring, provided our closest ever views, showing details as small as a house and confirming the complex interactions between the ring particles and Saturn's magnetic field and atmosphere. Ultimately, the imagery we have of Jupiter and Saturn transcends mere beauty. Every stripe, every storm, every geometric wonder, and every groove in the rings is a direct visual representation of underlying physical laws. The banding is a map of wind shear and convection. The Great Red Spot is a diagram of vortex dynamics and chemical interactions. Saturn's hexagon is a visible manifestation of wave patterns in a spinning fluid. The intricate ring structure is a precise record of gravitational resonances with orbiting moons. These worlds are not just objects to be admired, they are dynamic maps of physics, where the visual patterns we observe are the direct, inevitable result of mass, spin, temperature, and gravity operating on a scale we are only beginning to comprehend. They teach us that the universe is not random but ordered, and that its most magnificent art is always an expression of its most fundamental rules. If the gas giants show us the art of atmospheric physics, then nebulae offer us the most profound visual poetry of all, the story of stellar life and death itself. These vast, luminous clouds of gas and dust scattered throughout our galaxy are not just beautiful accidents, they are the fundamental cradles and graves of stars, and their imagery provides a direct window into the most dramatic chapters of cosmic evolution. Among the most iconic of these celestial portraits are the pillars of creation within the Eagle Nebula. Captured in stunning detail by the Hubble Space Telescope, these towering, ghostly structures resemble mythical stalagmites rising from a cosmic abyss. But what we are seeing is not stone. It is a cold, dense cloud of molecular gas and dust, light years long, being sculpted by an intense onslaught of ultraviolet radiation from nearby, massive, newborn stars. The pillars are simultaneously being eroded and revealed. The fierce stellar winds are boiling away the less dense material, while within the dark, dense knots at the tips of the pillars, the radiation is actually compressing the gas, triggering the gravitational collapse that will lead to the birth of new stars. This one image is a perfect snapshot of a cosmic cycle, destruction giving rise to creation, all frozen in a single, breathtaking moment. To truly read this image, however, we need to understand the language of its color. The famous Hubble portrait of the pillars is a masterclass in multi-wavelength observation. It is not a single photograph but a composite, where specific colors are assigned to light emitted by specific elements. The ethereal, red glow that seems to emanate from within the pillars comes primarily from ionized hydrogen. The intense ultraviolet light from the nearby hot stars strips electrons from the hydrogen atoms, and when those electrons recombine with protons, they emit a characteristic red light. The blue-green wisps that curl around the structures are emitted by singly ionized oxygen atoms, and the dark, opaque regions of the pillars, that is the dust itself, vast clouds of carbon and silicate grains, blocking the light from the brighter nebula behind it. This use of false color is not an artistic fabrication, it is a scientific translation. It allows us to visually separate the different components of the nebula, turning a beautiful picture into a detailed chemical and physical map. We can see where the energy from the stars is hitting the gas, what elements are present, and how the material is distributed. It transforms an object of awe into a rich dataset, a narrative written in light. But nebulae are not only about birth, they also chronicle the end of a star's life, and in a strangely beautiful form. For a star like our Sun, death is not a cataclysm but a graceful, slow unveiling. In its final stages, a Sun-like star will puff off its outer layers into space, creating a glowing shell of gas known as a planetary nebula. This name is a historical misnomer from early observers who thought their round shapes resembled planets, but we now know they are the dying breaths of stars. The Ring Nebula is a classic example, a perfect smoke-like circle of gas with a faint white dwarf star, the star's exposed dead core, visible at its center. The intricate shapes of these nebulae, from bipolar bubbles to complex, butterfly-like structures, are a visual puzzle. They hint at the complex processes occurring during the star's death throes, often influenced by the star's magnetic field or the presence of a companion star. The glowing gas, heated by the intense ultraviolet radiation from the hot white dwarf, reveals its composition: the reds of nitrogen and hydrogen on the outer edges, and the blue-greens of oxygen closer to the center. A planetary nebula is a star's final masterpiece, a brief, beautiful shroud that will eventually disperse, seeding the interstellar medium with the heavy elements forged in its core. elements that will one day become part of new stars, planets, and perhaps even life. For stars much more massive than the Sun, death is far more violent and spectacular. Their finale is a supernova, an explosion so brilliant it can outshine an entire galaxy. The remnant of such an explosion presents a completely different visual story. The Crab Nebula, the result of a supernova observed by Chinese astronomers in the year 1054, is a tangled web of glowing filaments. These filaments are the expanding debris of the shattered star, rushing outward at thousands of miles per second. The light we see is emitted as this debris slams into the surrounding interstellar medium, creating immense shock waves that heat the gas and cause it to glow. The colors here again tell a specific story. The reddish filaments are primarily hydrogen, the outer layers of the original star, while the bluish, filamentary haze in the nebula's center is synchrotron radiation, emitted by electrons spiraling at nearly the speed of light in the powerful magnetic field generated by a pulsar, the rapidly spinning neutron star that is the crushed core of exploded star. The Crab Nebula is not a serene shroud. It is a chaotic, dynamic crime scene, a visual testament to a stellar catastrophe that is also an act of cosmic recycling. Within this expanding cloud, the intense heat and pressure of the explosion forge heavy elements like gold, silver, and uranium, scattering them across space. Together, these different types of nebulae form a complete visual biography of stars. An emission nebula like the Orion Nebula shows us the bustling stellar nursery where stars are born from collapsing clouds of gas and dust. The serene beauty of a planetary nebula shows us the peaceful, final exhalation of a common star, returning its enriched material to the galaxy. And the chaotic filaments of a supernova remnant show us the violent death of a massive star, an explosion that seeds the cosmos with the elements necessary for planets and life. This narrative from cradle to grave is not locked away in textbooks or complex equations. It is displayed across the night sky in a visual language of color, shape, and light. These images make the abstract, billion-year life cycles of stars immediate, tangible, and awe-inspiring. They allow us to witness the grand recycling program of the universe, where death gives way to new birth, and where the end of one star is the beginning of countless possibilities. This cycle of creation and destruction hinges on a force we have not yet seen, a mysterious presence that holds the entire cosmic tapestry together. But as we trace the beautiful life cycles of stars and galaxies, a profound and unsettling mystery emerges, one that challenges our very understanding of what the universe is made of. For all the brilliant nebulae, swirling galaxies, and vast clusters we can see, they represent only a tiny fraction of what is actually there. The overwhelming majority of the universe's mass is completely invisible. We call this elusive substance dark matter, and its existence is inferred not from the light it emits, but from the irresistible gravitational pull it exerts on everything we can see. The evidence for dark matter began with observations of how galaxies move. In the 1930s, astronomer Fritz Zwicky was studying the Coma Cluster, a massive collection of galaxies. By measuring the velocities of the galaxies orbiting the cluster's center, he could calculate how much mass must be present to hold the cluster together with gravity. The result was staggering. The mass required was hundreds of times greater than the mass of all the visible stars and gas combined. It was as if the entire cluster was embedded in a vast, massive halo of something unseen. Decades later, Vera Rubin provided even more compelling evidence by studying the rotation of individual spiral galaxies. She found that stars at the outer edges of galaxies were orbiting just as fast as those near the center. According to the laws of gravity, This should be impossible unless there was a huge amount of invisible mass distributed far beyond the galaxy's visible disk, providing the extra gravitational glue to keep those fast-moving stars from flying off into space. The visible galaxy, it turned out, was just the bright tip of a much larger, much darker iceberg. So how do you map something that emits no light, reflects no light, and seems to interact with normal matter only through gravity? You watch how it bends the very fabric of space itself. This is where one of Einstein's most dramatic predictions comes into play: gravitational lensing. His theory of general relativity tells us that mass warps the space around it. A massive object like a galaxy cluster acts like a lens in space-time, bending the path of any light that passes near it. When astronomers point the Hubble Space Telescope at a massive cluster, they sometimes see a bizarre and beautiful sight. The background galaxies behind the cluster are not just magnified, they are stretched and distorted into long, faint arcs of light, like reflections in a funhouse mirror. In extreme cases, a single distant galaxy can be lensed into multiple images, appearing as identical copies around the cluster's edges. This gravitational lensing is a direct visual effect of the cluster's total mass, both visible and invisible. But the real breakthrough in visualizing dark matter came when scientists realized they could use this effect to map its distribution with astonishing precision. By carefully analyzing the subtle distortions of thousands of faint background galaxies, a technique called weak gravitational lensing, astronomers can create a map of the mass responsible for the warping. They can calculate where the mass must be and how much of it there is. The resulting visualizations are some of the most powerful in all of modern cosmology. You will often see a composite image of a galaxy cluster. In the foreground, the brilliant galaxies of the cluster are shown in their natural, visible light colors. But overlaying this scene is a translucent, ethereal blue haze. This blue haze is not something the telescope directly photographed. It is a computer-generated map of the inferred dark matter distribution, based entirely on the lensing distortions. It shows the invisible scaffolding, the hidden skeleton upon which the visible universe is built. These maps reveal a cosmic architecture that is both elegant and strange. The dark matter forms a vast, diffuse halo that envelops the entire galaxy cluster, extending far beyond the outermost visible galaxies. Within this halo, the dark matter is not smooth. It clumps and folds, tracing out a complex web of filaments. The visible galaxies we see are not randomly scattered. They are nestled within the densest knots of this dark matter web, like dew drops on an invisible spider web. This visual evidence is transformative. Dark matter ceases to be an abstract equation or a theoretical necessity. It becomes a visual problem. We can see its gravitational signature so clearly, its effects so dramatically painted across the sky in the form of stretched and distorted galaxies, that its existence becomes almost tangible. The blue haze on those composite images is a ghostly presence, a map of the unknown. It is the universe showing us that what we see is not all there is, and that the greatest forces shaping our cosmos are, for now, hidden in plain sight. For generations, the black hole existed as a fantastical monster in the equations of theoretical physics, a prediction of Einstein's theory of gravity so extreme it seemed it might forever remain in the realm of imagination. A place where gravity becomes infinite, where space and time cease to have any meaningful structure, and from which not even light can escape. How could you ever see such a thing? The very definition of a black hole is its invisibility. But in April of 2019, a team of scientists from the Event Horizon Telescope collaboration did the seemingly impossible. They presented the world with a picture, not an artist's impression, not a simulation, but a direct image of the shadow of a supermassive black hole at the heart of the distant galaxy Messier 87, 55 million light-years away. This fuzzy, fiery donut, instantly recognizable around the globe, was a monumental achievement in visual poetry, turning one of the universe's most abstract concepts into a tangible reality. So, what exactly are we looking at in this historic image? It is crucial to understand that we are not seeing the black hole itself. That remains forever hidden behind its point of no return, the event horizon. Instead, we are seeing its shadow, a dark silhouette cast against a brilliant backdrop of light. This backdrop is the black hole's accretion disk, a swirling, superheated maelstrom of gas and dust that is being pulled inexorably toward the event horizon. As this material spirals inward, friction heats it to temperatures of billions of degrees, causing it to glow intensely across the entire electromagnetic spectrum. The dark central region is the black hole's shadow, and it is about 2.5 times larger than the actual event horizon. This size difference is the key to the image. It is caused by the black hole's phenomenal gravity, which acts like a lens, bending the light paths around it. Light from the accretion disk that would normally travel away from us is bent by gravity so severely that it is redirected into our telescopes. However, light paths that stray too close to the event horizon cross the point of no return and are swallowed. This creates a dark absence, a shadow, surrounded by a bright ring of bent light. The image is a perfect visual manifestation of Einstein's general theory of relativity, a diagram of warped spacetime made real. Capturing this image from 55 million light-years away was a Herculean task that required a telescope of literally planetary scale. The resolution needed to see such a small, distant object is akin to reading a newspaper in New York from a sidewalk cafe in Paris. No single telescope on Earth possesses that kind of power. The ingenious solution of the Event Horizon Telescope collaboration was to synchronize a global network of 8 radio observatories, from the high mountains of Hawaii and Chile to the frigid landscapes of the South Pole and the Sierra Nevada in Spain. By using a technique called Very Long Baseline Interferometry, or VLBI, these individual dishes were linked together to act as one single Earth-sized telescope. During a specific window of time in April of 2017, all of these observatories turned their gaze toward M87, collecting petabytes of raw data on the radio waves emanating from the black hole's vicinity. Because they were not physically connected, each site recorded its data onto high-performance atomic clocks, and the hard drives were later physically flown to central processing centers where supercomputers correlated the signals. It was a digital version of a giant photographic plate assembled from data gathered across the globe. The result of this observation was not a ready-made photograph. What the telescopes collected were not pixels, but measurements of the complex relationships between the radio waves received at each pair of telescopes across the network. This left the collaboration with a monumental puzzle, a set of mathematical clues from which the actual image had to be reconstructed. Several independent teams used different algorithms to translate this sparse data into a visual picture, a process akin to trying to reconstruct a song from a handful of scattered notes. The fact that all the teams produced a similar image, a bright ring with a dark center, was the powerful confirmation that they were seeing a real astronomical object and not an artifact of their processing. The final, now iconic image we saw was a representative snapshot, an average of these reconstructions, painstakingly built from the faint whispers of radio waves that had traveled for 55 million years. This single picture is far more than a trophy of technological prowess. It is a fundamental test of our understanding of physics under the most extreme conditions imaginable. The size and shape of the shadow are direct predictions of general relativity, and the M87 image matched those predictions with remarkable accuracy. It visually confirms that massive, compact objects really do warp spacetime in exactly the way Einstein described over a century ago. But perhaps more importantly, the image opens a new chapter in observational astronomy. It gives us a new tool to probe the mysteries of black hole jets, like the powerful one shooting out from M87, and to study the chaotic dynamics of accretion flows. It also raises profound new questions about the nature of the event horizon and what happens to information that falls inside. The shadow is a boundary, a gateway to a realm where our current laws of physics break down. By making this boundary visible, the Event Horizon Telescope has not closed a chapter on black holes. It has given us our first clear look at the doorway to the unknown, inviting us to peer deeper into the darkness and question what lies beyond the limits of our vision. If the image of a black hole's shadow represents the edge of our observational capabilities for singular objects, then the cosmic microwave background takes us to the very limit of time itself, to a moment when the entire observable universe was smaller than a single atom. This is not a portrait of a distant object. It is a full-sky snapshot of the cosmos in its infancy, a fossilized echo of the Big Bang that surrounds us in every direction. To understand this, we need to travel back to a time when the universe was not transparent, but was a searing, opaque fog. For the first 380,000 years of its existence, the cosmos was so hot and dense that it was filled with a plasma of protons, electrons, and photons. Light particles or photons could not travel freely. They would instantly bounce off or scatter from the dense soup of charged particles like headlights in a thick cosmic fog. The universe was a glowing, blindingly bright prison for light. Then, in a pivotal moment, the universe expanded and cooled just enough for a fundamental transition to occur. The temperature dropped below about 3,000 degrees Kelvin, allowing electrons to combine with protons to form the first neutral hydrogen atoms. In this sudden neutralization, the fog lifted. The charged particles that had been scattering the light were now bound into neutral atoms, and the photons, for the first time, could stream freely across the universe. This event is called recombination, and the moment the universe became transparent is known as the surface of last scattering. The light that was released at that exact instant has been traveling ever since, stretched and cooled by the relentless expansion of space over the ensuing 13.8 billion years. What was once a brilliant flash of visible and infrared light has been redshifted by a factor of about 1,100, all the way down to the microwave part of the spectrum. This is the cosmic microwave background radiation. It is not coming from one location. It is coming from everywhere, from the most distant void to the space between the stars in our own galaxy. It is the oldest light in the universe, and it fills all of space. So, what does this ancient light actually look like? The maps produced by satellites like NAS, a Wilkinson Microwave Anisotropy Probe, or WMAP, and the European Space Agency's Planck mission, are not traditional photographs in any sense. They are maps of tiny temperature variations across the entire sky. If you could see the universe in microwave eyes, the CMB would appear as an almost perfectly uniform glow, with a temperature of just 2.7 degrees above absolute zero. But when scientists remove this uniform background and exaggerate the tiny differences, an extraordinary pattern emerges. The sky is mapped as a mottled tapestry of red and blue speckles, often compared to the static on an old television set or the texture of a speckled egg. Each of those speckles represents a minute fluctuation in temperature, a tiny patch of the sky that is ever so slightly warmer or cooler than the average. The differences are incredibly small, varying by only about 100 millionths of a degree, but these minuscule imperfections are, without exaggeration, the most important structures in the history of the cosmos. These tiny temperature differences are not random noise, they are the cosmic genetic code. They are the imprint of density variations in the primordial plasma. A slightly warmer spot in the CMB corresponds to a region that was ever so slightly denser than average. A cooler spot was a slightly emptier region. In the fiery early universe, gravity was already at work. Those overdense regions had slightly stronger gravity, which began to pull in more matter. Over hundreds of millions of years, these tiny seeds grew, snowballing through gravitational attraction. The slightly denser patches collapsed to form the first stars and galaxies, while the slightly emptier regions evolved into the vast cosmic voids we see today. The entire large-scale structure of the universe, the great cosmic web of galaxy clusters, filaments, and voids, is a direct result of the pattern imprinted on the CMB. The speckled egg map is the blueprint for everything that exists. The precision with which we have measured this blueprint is what makes the CMB such a powerful tool for cosmology. By analyzing the statistical properties of these temperature fluctuations, their sizes, their distribution, their correlations, scientists can extract a staggering amount of information about the universe's fundamental properties. It is from the CMB that we have our most precise measurement of the age of the universe, 13.8 billion years. It tells us the universe is geometrically flat on large scales, meaning that the rules of Euclidean geometry we learned in school hold true for the cosmos as a whole. Most profoundly, the CMB data allows us to take a complete inventory of the cosmos. It reveals that the familiar atoms that make up stars, planets, and us constitute only about 5% of the total content of the universe. About 27% is the mysterious dark matter that holds galaxies together, and a whopping 68% is the even more enigmatic dark energy, which is causing the expansion of the universe to accelerate. The CMB is the ultimate historical document, a single image that encodes the universe's birth, its composition, and its ultimate fate. The Planck satellite's map is so detailed that it has become a testing ground for the very theory of the Big Bang itself, specifically a component called cosmic inflation. This theory proposes that the universe underwent an unimaginably rapid exponential expansion in the first fraction of a second after the Big Bang. This inflationary period would have stretched quantum fluctuations from the subatomic world to cosmic sizes, planting the seeds that would later become the temperature variations in the CMB. The pattern we see in the Planck data matches the predictions of inflation with remarkable accuracy, providing our strongest evidence that this dramatic event actually occurred. However, the incredible precision of the data has also revealed potential anomalies, subtle features in the pattern that don't quite align with the simplest models. These could be mere statistical flukes, or they could be hints of new physics, clues to a reality that is even stranger than we currently imagine. The cosmic microwave background, therefore, is not a closed book. It is a living dataset, a baby picture that we are still learning to read, and its faint whispers from the dawn of time continue to guide us toward a deeper understanding of the cosmos from which we emerged. For centuries, the very existence of planets around other stars was a matter of pure speculation, a philosophical question without a visual answer. Our own solar system seemed like a possible cosmic accident. But in the last few decades, that question has been transformed by visual evidence so compelling it has reshaped our understanding of our place in the galaxy. We have moved from wondering if other worlds exist to mapping the dynamics of entire alien solar systems, And much of this revolution has been driven not by traditional photographs, but by interpreting the subtle, telltale signs that planets leave on the light of their parent stars. One of the most powerful and prolific techniques for this cosmic detective work is the transit method. Imagine watching a distant street lamp from miles away. If a tiny gnat were to fly directly in front of the bulb, you would never see the insect itself, but you might notice an almost imperceptible flicker in the light. Now scale this up to a planetary level. When a distant exoplanet orbits its star and from our vantage point passes directly in front of the stellar disk, it blocks a tiny fraction of the star's light. This event is called a transit. The star does not visibly dim to our eyes, but our sensitive instruments can detect this minute drop in brightness. When astronomers plot these precise measurements over time, they create a graph known as a light curve. This graph is where the magic happens. A light curve is a visual story. For most of the time, it is a flat, steady line representing the star's constant brilliance. Then, at regular, predictable intervals, a distinct U-shaped dip appears. The depth of that dip is directly proportional to the size of the planet. A larger planet blocks more light, creating a deeper dip. The duration and frequency of the dips reveal the planet's orbital period, its year. This elegant technique, used to spectacular effect by missions like NASA's Kepler Space Telescope, has given us thousands of confirmed exoplanets by turning abstract photometric data into a clear, repeating signature of an orbiting world. But the transit method can reveal even more surprising details. By analyzing the starlight that filters through the planet's atmosphere during the transit, a technique called transmission spectroscopy, astronomers can discern the composition of the alien air. Specific molecules in the atmosphere, like water vapor, sodium, or methane, absorb characteristic wavelengths of the star's light. As the planet transits, the star's light, when split into a spectrum, will show tiny, additional dips at those specific wavelengths. The resulting data is visually translated into an atmospheric profile, a bar chart of chemical abundances that turns a distant point of light into a world with a potentially hazy, cloudy, or clear sky. This transforms a simple light curve dip into a rich, multi-layered narrative about the planet's conditions. While the transit method is incredibly effective, it is an indirect view. The ultimate goal, the most direct form of visual poetry, is to actually see these worlds. This is the realm of direct imaging, a challenge so immense it was once thought to be nearly impossible. The central problem is one of contrast. A planet is millions of times fainter than its host star and orbits incredibly close to it from our distant perspective. It is like trying to spot a firefly hovering next to a massive, brilliant searchlight from 1,000 miles away. To overcome this, astronomers use ingenious instruments called coronagraphs, which are masks inside the telescope that physically block the blinding light of the central star. With the star's glare suppressed, the much fainter light of orbiting planets can be detected. Systems like HR 8799 have become icons of this technique. In stunning images, we see not just one, but 4 distinct dots of light, each a gas giant planet several times the mass of Jupiter, orbiting at great distances from their star. These are not graphs or inferences. These are actual portraits, albeit single pixels of light. Time-lapse observations of such systems show these pixels slowly moving, tracing out their long orbital paths over years of observation. It is a breathtaking validation, a direct visual confirmation of entire planetary systems in motion. This visual confirmation of orbital motion finds a beautiful and fundamental parallel in the dance of binary stars. For many stars, our Sun's solitary nature is the exception, not the rule. A majority of stars in the galaxy are born in pairs or multiples. gravitationally bound to each other for life. By observing these binary systems over many years, we can chart the precise elliptical paths each star takes around their common center of mass. This celestial waltz is a pure visual demonstration of Newton's and Einstein's laws of gravity in action. The period of the orbit and the size of the orbits allow astronomers to calculate the stars' masses with extraordinary accuracy. Binary stars provide the cosmic scales against which we can weigh stars, a fundamental parameter that would be much harder to determine for solitary stars. Watching a binary pair complete their dance is to see gravity itself made visible, a clockwork mechanism on an astronomical scale. Together, these visual techniques, the rhythmic dips of transits, the faint pixels of direct images, and the precise orbits of binary stars, have transformed the abstract idea of other solar systems into a concrete, vibrant reality. We now know that planets are not rare, they are commonplace, outnumbering the stars in our galaxy. We have discovered an incredible diversity of worlds, hot Jupiters orbiting blisteringly close to their stars, super-Earths larger than our own but smaller than Neptune, and planets orbiting in the habitable zone, the region where temperatures might allow for liquid water. This visual evidence fuels the most profound mystery of all, the search for life elsewhere. Every new exoplanet characterized, every atmosphere studied, brings us closer to answering the ancient question of whether we are alone. The visual poetry here lies in the data itself, in the ability to translate subtle fluctuations in light into a grand narrative of cosmic companionship, suggesting that our own pale blue dot is just one among a vast and varied family of worlds. While we often picture asteroids as solid, monolithic rocks drifting silently through the void, the reality revealed by our closest encounters is far stranger and more revealing. The missions that have journeyed to these ancient worlds have returned images that rewrite our understanding of what they are. The OSIRIS-REx mission to asteroid Bennu and the Hayabusa 2 mission to asteroid Ryugu provided our first intimate views of these carbon-rich relics, and what they showed was astonishing. Instead of solid bedrock, both asteroids were revealed to be what scientists call rubble piles. They are not single, cohesive bodies, but rather loose collections of boulders, rocks, and gravel, held together by the faintest whisper of their own gravity. High-resolution images from the spacecraft showed surfaces that are incredibly rough, littered with car-sized and even house-sized boulders, with very little of the fine, sandy dust or regolith that covers the Moon. This distinctive texture is a direct visual clue to their violent history. These asteroids are likely the remnants of a much larger parent body that was shattered in a catastrophic collision billions of years ago. The debris from that impact then slowly reaccumulated under gravity, but without the pressure and heat to fuse into a solid rock, forming these fragile, porous piles. When the OSIRIS-REx spacecraft attempted to touch down on Bennu to collect a sample, its arm actually sank several centimeters into the surface, as if dipping into a ball pit, visually confirming the astonishing lack of structural integrity. These are not rugged mountains in space, they are delicate cosmic sandcastles. The visual story of these asteroids, however, goes far beyond their surprising structure. The presence of certain minerals, identified by their light-reflecting properties, tells a story of water. Both Bennu and Ryugu show spectral signatures of clay minerals that can only form in the presence of liquid water. This does not mean these asteroids had oceans. Rather, it suggests their much larger parent body did, early in the solar system's history. The visuals thus paint a picture of a world that was once warm and wet enough for chemical reactions to alter its primordial rock, creating the complex building blocks of chemistry. When a spacecraft like Hayabusa 2 fired a small copper projectile into Ryugu's surface to stir up material for collection, the resulting images were equally telling. The impact did not create a crater in solid rock, but instead excavated a dark, reddish material from beneath the surface. This color change indicated that the asteroid's exterior has been darkened and reddened by billions of years of exposure to the relentless bombardment of cosmic radiation and solar wind, a process called space weathering. The fresh, unweathered material underneath was a glimpse into the asteroid's pristine interior, a sample of the solar system's original ingredients, perfectly preserved in a deep freeze since its formation. Every boulder, every crater, and every color variation in these images is a page from a geological history book that dates back to the very dawn of our planetary system. In stark contrast to the dark, rubble-pile asteroids, comets present a completely different kind of visual poetry. Where asteroids are relatively inert, comets are dynamic and alive. The European Space Agency's Rosetta mission provided the most detailed portrait ever of a comet, as it spent 2 years orbiting the bizarre world known as 67P, Churyumov-Gerasimenko. The first images that came back were utterly surreal. The comet was not a round ice ball as often depicted. It was shaped like a rubber duck with 2 distinct lobes connected by a thin, dusty neck. This peculiar shape immediately sparked scientific debate. Was it the result of a gentle merger between 2 separate cometesimals in the early solar system, or did a single body erode in the middle over eons of sun-grazing orbits? The visuals alone posed a fundamental question about cometary formation and evolution. The surface of 67P was a landscape of dramatic extremes. Rosetta's cameras captured towering cliffs, some nearly a kilometer high, with surfaces that looked like solidified foam, pitted with circular pits and crisscrossed by enormous fractures. Other regions were covered in smooth, dusty plains that resembled wind-blown sand dunes. Though there is no wind on a comet, these dunes were likely formed by dust transported across the surface during the comet's violent outbursts of gas. And it is this activity that defines the visual drama of a comet. As Rosetta followed 67P on its journey closer to the Sun, the spacecraft witnessed the comet awakening. Patches of ice on the surface, warmed by the increasing solar radiation, would transform directly from solid ice into gas, a process called sublimation. This escaping gas, dragging dust with it, created spectacular jets that erupted from the comet's nucleus like geysers. Rosetta captured these jets in stunning detail, sometimes seeing multiple firings simultaneously, carving out the comet's surface and contributing to its thin, temporary atmosphere or coma. The visuals made the abstract concept of a comet's tail intimately real. We could see the very process that creates those magnificent, sweeping tails that have captivated humanity for millennia. The jets are the engines. The sunlight and solar wind then push that gas and dust away, forming the distinct tails that can stretch for millions of kilometers across the inner solar system. Rosetta's images showed a world in constant, slow-motion transformation, its very substance being boiled away into space with each close pass around the Sun. Together, the visual portraits from these missions to asteroids and comets have turned the mystery of our own origins into a tangible, visual pursuit. These small, primitive bodies are the leftover building materials from the construction of the giant planets. They are the bricks and mortar that never got used, preserved in the deep freeze of the outer solar system. The discovery of water-bearing minerals on asteroids and the confirmation of abundant water ice on comets provides a compelling visual and chemical clue to one of Earth's oldest mysteries. Where did our oceans come from? The leading theory, supported by this imagery, is that after Earth formed, it was too hot to retain water. The vast volumes of water that now fill our oceans were likely delivered later by a bombardment of these very same water-rich asteroids and comets. Furthermore, missions like OSIRIS-REx and Rosetta have both detected the presence of complex organic molecules, the carbon-based building blocks of life on these objects. This visual and analytical evidence suggests that these celestial delivery trucks may not have just brought the water for our oceans, but also the fundamental ingredients for life itself. When we look at the craggy, boulder-strewn surface of Bennu or the jet-spewing visage of Comet 67P, we are not just looking at distant curiosities. We are looking at potential architects. They are visual representations of the process that may have seeded our planet with the very elements necessary for a biosphere to flourish, making our search for our own beginnings a journey that is now guided by the light reflected from these ancient, wandering worlds. Yet for all its power, a supernova is not the final word in stellar annihilation. There exists an event in the cosmos so ferociously energetic, so blindingly luminous, that it makes even a supernova seem like a flickering candle. These are gamma-ray bursts, the universe's most powerful known explosions. While a supernova might outshine its entire host galaxy for a few weeks, a gamma-ray burst can, for a few fleeting seconds, outshine the combined light of every star in the observable universe. Their name comes from the form of their initial, devastating energy release, an intense, focused beam of the highest energy photons, gamma rays. This is not a gentle unfolding of light. It is a cosmic scream, a torrent of radiation so powerful that if one were to occur within a few thousand light-years of Earth, it could strip away our ozone layer and trigger a mass extinction. For decades after their accidental discovery by military satellites in the 1960s, these bursts were one of astronomy's greatest mysteries, appearing randomly from all directions and vanishing before their positions could be pinpointed. The breakthrough in understanding gamma-ray bursts came when scientists developed the ability to see what happened after the initial flash. As the intense gamma-ray beam slams into the surrounding interstellar material, it creates a secondary phenomenon known as an afterglow. This afterglow radiates at longer, less energetic wavelengths like X-ray, optical, and radio light. Unlike the initial burst that lasts for mere seconds, the afterglow can linger for days or even weeks. The pivotal moment arrived when telescopes like the Bepo-SX satellite could rapidly locate the X-ray afterglow of a burst and then relay those coordinates to optical telescopes on the ground. For the first time, astronomers could swivel their most powerful instruments to the precise spot in the sky and capture an image of the afterglow in visible light. These images were often faint, but they were enough to pinpoint the burst's origin to a specific, incredibly distant galaxy. This visual evidence was the key that unlocked the mystery. It confirmed that gamma-ray bursts are not local phenomena but cosmological events, occurring billions of light-years away, which meant their true energy output was almost incomprehensibly vast. We now understand that there are two primary types of these cosmic detonations, each with a distinct visual signature linked to its cause. Long-duration gamma-ray bursts, those lasting more than 2 seconds, are now known to be the death cries of the most massive stars in the universe. They are essentially a supernova on steroids. When a star dozens of times more massive than the Sun exhausts its fuel, its core does not just collapse into a neutron star, it collapses directly into a black hole. The infalling material forms a swirling accretion disk around the newborn black hole, and through processes still not fully understood, powerful jets of plasma are launched from its poles at nearly the speed of light. It is these jets beamed directly at us that we see as the gamma-ray burst. If we are positioned off-axis, we might only witness the associated supernova, a brilliant but less focused explosion. But when we look down the barrel of the jet, we witness the ultimate stellar catastrophe. The visual story here is one of focused annihilation, where the death of a star is not a symmetrical expansion but a directed beam of pure energy. The second type, short-duration gamma-ray bursts lasting less than 2 seconds, tells a different, equally dramatic story. These are thought to be the result of a different kind of merger, one we will explore in more detail later, the collision of two ultra-dense stellar remnants such as neutron stars. When these incredibly massive objects spiral into each other, they too can create a black hole surrounded by a torus of hot debris, launching a similar, albeit shorter, jet of gamma radiation. The afterglow from these events also appears in visible light, allowing us to trace them back to their host galaxies. Interestingly, these galaxies are often much older and have less ongoing star formation, which fits the theory that it takes a long time for two neutron stars to slowly spiral together through the emission of gravitational waves. The imagery of these afterglows, therefore, is not just a pretty picture. It is a forensic tool that helps astronomers distinguish between the two violent formation mechanisms of these extraordinary events. The visual poetry of these explosions, from the expanding rings of a supernova light echo to the faint, fading pinpoint of a gamma-ray burst afterglow, transcends mere spectacle. It provides the crucial data for one of the most profound ideas in all of science, cosmic recycling. The universe began with only the lightest elements, hydrogen, helium, and a trace of lithium. Every other element on the periodic table, every atom of oxygen we breathe, the calcium in our bones, the iron in our blood, had to be forged somewhere. The ordinary nuclear fusion in the cores of stars can create elements up to iron, but to create anything heavier, the gold in a wedding ring, the uranium in a power plant, the iodine in our bodies requires a more violent process. These heavy elements need a rapid capture of neutrons, an event that can only occur in the most extreme environments. For decades, the leading candidate for this creation was the supernova explosion itself. The incredible heat and density in the expanding shockwave could provide the necessary conditions to seed the universe with these precious metals. However, the story has become more nuanced with the study of gamma-ray bursts, particularly the short-duration kind linked to neutron star mergers. When two neutron stars collide, they spray a cloud of neutron-rich material into space. In this environment, atoms are bombarded with neutrons, rapidly building up heavier and heavier elements in a process known as rapid neutron capture, or the R process. This cataclysm produces vast quantities of gold, platinum, and other heavy elements. The visual and spectroscopic analysis of the afterglow from a neutron star merger, an event we will return to, has provided strong evidence for this, showing spectral signatures consistent with the presence of these newly forged elements. The imagery of stellar death, therefore, is directly linked to the origin of the elements that make up our world and ourselves. When we look at a supernova remnant or the location of a gamma-ray burst, we are not just looking at a destructive force. We are looking at a cosmic forge. We are witnessing the moment that scattered the raw materials for future planets and ultimately for life. The calcium in your teeth, the oxygen in your lungs, and the iron in your blood were all blasted into the cosmos by a star that died a violent death long before our sun was even born. We are quite literally stardust, and these violent, beautiful images are the records of our own deepest ancestry. For over 4 centuries, astronomy has been the science of light. We have built ever larger telescopes to gather more photons, to see farther and in greater detail. But light, for all its wonders, is only one messenger from the cosmos. Imagine trying to understand a symphony by watching the violinists alone. You would miss the deep resonance of the cello, the crash of the cymbals, the entire sonic landscape that gives the music its full emotional power. In 2017, our understanding of the universe underwent a similar transformation. We learned to listen. We opened a new ear to the cosmos, one that senses not light, but the very fabric of space-time itself. This new sense detects gravitational waves, the ripples in reality predicted by Einstein a century ago, and in doing so, it launched a revolutionary era known as multi-messenger astronomy. The instruments that made this possible are marvels of engineering unlike any traditional telescope. The LIGO observatories in the United States and their European counterpart, VIRGO, are essentially the most precise rulers ever constructed. Each consists of two long vacuum tubes, several kilometers in length, arranged in an L shape. A laser beam is split and sent down each arm, bouncing off mirrors to travel back and forth. In normal circumstances, the beams return perfectly in sync, canceling each other out. But when a gravitational wave passes through the Earth, it does something extraordinary. It subtly stretches space in one direction and compresses it in the perpendicular direction. This infinitesimal stretching and squeezing, a distortion far smaller than the width of a proton, changes the length of the arms by a minuscule amount. This is enough to make the laser beams fall out of sync, creating a tiny, measurable flicker in the light. LIGO is not a giant eye looking up. It is a massive ear feeling the vibrations of spacetime as cosmic waves wash over our planet. On August 17, 2017, that ear heard a sound that would change astronomy forever. The LIGO and VIRGO detectors registered a gravitational wave signal that was different from all the previous ones. Earlier detections had been the deep thuds of black holes merging, events that produced no light. This new signal was a rising chirp, lasting about 100 seconds. Its characteristics pointed unmistakably to the source. The final, frantic dance of two neutron stars, the ultra-dense, city-sized cores of dead stars, spiraling together at nearly the speed of light before colliding. But the real revolution began moments after the chirp ended. Unlike a black hole merger, the collision of neutron stars was predicted to produce a brilliant, detectable flash of light. Crucially, the gravitational wave signal provided something a mere light signal never could: a precise location in the sky. Within minutes, an automated alert was sent to astronomers around the world, and telescopes of every kind from every continent and in orbit swiveled to a small patch of sky in the constellation Hydra. What they saw just 11 hours after the gravitational wave detection was a new point of light, a faint bluish pinprick in a galaxy known as NGC 4993, about 130 million light-years away. This was the kilonova. As the name suggests, it was 1,000 times brighter than a typical nova. The visual story of this event unfolded over days. The initial blue color came from the incredibly hot, expanding cloud of material ejected during the merger, a cloud rich in heavy elements like cesium and tellurium. As the cloud expanded and cooled, its glow shifted to red as heavier, slower decaying elements like platinum, gold, and uranium began to dominate the emission. Telescopes across the spectrum, from gamma-ray satellites to radio observatories, tracked this evolution, creating a multi-wavelength time lapse of the event. The Fermi Gamma-Ray Space Telescope had even detected a short gamma-ray burst just 2 seconds after the gravitational wave signal, confirming the long-held theory that these immense explosions are indeed linked to neutron star mergers. For the first time in history, we had not just seen an event and not just heard it, we had done both simultaneously. the scientific payoff was immediate and profound. The visual and spectroscopic data from the kilonova provided the long-sought proof that neutron star mergers are primary cosmic forges for the heaviest elements in the universe. The observations revealed signatures of newly synthesized material, including an amount of gold equivalent to several times the mass of our entire planet, and even more platinum. This single event demonstrated that the precious metals in our jewelry and the radioactive elements in our medical equipment are created in these violent, distant collisions. The combination of gravitational waves and light created a complete picture. The gravitational waves told us about the masses of the objects and the dynamics of their final moments. The light told us about the composition and the aftermath of the explosion. It was like watching a silent movie for your entire life, and then suddenly hearing the dialogue, the sound effects, and the musical score all at once. The narrative was no longer incomplete. This event, officially known as GW170817, marked the true dawn of multi-messenger astronomy. It proved that the most profound cosmic mysteries cannot be solved by light alone. Some events are too dark, too hidden, or too fundamentally tied to the fabric of gravity to reveal all their secrets through electromagnetic radiation. By learning to sense the vibrations of space-time, we have gained a completely new way to perceive the universe. We are no longer silent observers of a distant light show. We are now participants in a full sensory experience, feeling the tremors of cosmic catastrophes as we watch their light wash over us. This new sense allows us to probe the most extreme environments, from the warped space-time around black holes to the crushing density of neutron stars, with a clarity we never thought possible. It is a reminder that to understand the cosmos, we must be willing to use every tool at our disposal, to listen as intently as we look, and to feel the universe's deepest rhythms as well as see its most brilliant light. As we learn to sense the universe through gravity and light, we begin to see a deeper order emerging from the cosmic chaos. When we look up at a dark sky, the galaxies appear as a random scattering of faint, fuzzy lights. But just as a naturalist learns to classify the flora and fauna of a forest, astronomers have developed a way to bring order to this celestial menagerie. The key to unlocking the life stories of these island universes lies not in complex data, but in their most basic and beautiful characteristic, their shape. This visual taxonomy, elegantly organized by the famed Hubble tuning fork diagram, turns a seemingly chaotic sky into a gallery of galactic forms, each shape a direct clue to a galaxy's history, its dynamics, and its ultimate fate. The most iconic and picturesque members of the galactic family are the spiral galaxies. Imagine a colossal pinwheel spinning silently in the void, its arms traced out by the brilliant blue light of newly formed, massive stars and the glowing pink of stellar nurseries. This is the signature of a spiral galaxy, like the magnificent Messier 101, also known as the Pinwheel Galaxy. The Hubble tuning fork diagram places these galaxies on the central prong, classifying them based on the tightness of their spiral arms and the size of their central bulge. But these arms are more than just decoration, they are the engines of creation. The graceful spiral pattern is actually a density wave, a cosmic traffic jam that moves through the galaxy's disk. As clouds of gas and dust enter this wave, they are compressed, triggering the gravitational collapse that leads to the birth of new stars. This is why the arms appear so bright. They are bustling hubs of stellar activity. A large, prominent central bulge, as seen in galaxies like Messier 81, indicates an older population of stars, suggesting a more settled evolutionary state. In contrast, a galaxy with a small bulge and wide, loose arms is a hotbed of ongoing creation. The very structure of a spiral galaxy, therefore, is a visual timeline, its shape revealing the balance between ancient stellar populations and vibrant, ongoing star formation. On the opposite side of the Hubble tuning fork, we find a class of galaxies that could not be more different, the ellipticals. If a spiral galaxy is a vibrant, star-forming metropolis, an elliptical galaxy is a quiet, aging retirement community. These galaxies possess no disk, no arms, no discernible internal structure. Through a telescope, they appear as smooth, featureless ovals or spheres of light, fading gently away at the edges. They are composed overwhelmingly of older, redder stars, with very little of the cold gas needed to form new generations. A prime example is Messier 87, the giant elliptical galaxy at the heart of the Virgo cluster, which also houses the supermassive black hole we imaged. Ellipticals range dramatically in size, from dwarf spheroids only slightly larger than a globular cluster to true giants like M87, which contains trillions of stars and exerts a dominant gravitational influence over its entire cluster. Their smooth, amorphous shape is a direct result of their violent history. Astronomers believe that most large ellipticals are the products of galactic mergers. When two spiral galaxies of similar size collide, their orderly rotational motion is disrupted by gravitational interactions. The stars, which are so far apart that they rarely actually hit each other, are thrown into random, chaotic orbits. The gas clouds do collide, triggering a final, furious burst of star formation that quickly consumes the remaining fuel. The end result is a vast, spherical swarm of stars following random paths, a serene-looking elliptical galaxy that bears the quiet scars of a tumultuous past. But what about the galaxies that do not fit neatly into either category? The Hubble tuning fork has a final category for these outliers: irregular galaxies. These are the cosmic misfits, galaxies with a chaotic, fragmented structure that shows no clear spiral or elliptical form. Often, this irregularity is a sign of youth or, more commonly, a sign of a recent gravitational encounter. The Large and Small Magellanic Clouds, two small companion galaxies to our own Milky Way visible from the southern hemisphere, are classic irregulars. Their distorted shapes are likely the result of the relentless gravitational tug of war with our much larger galaxy. They are rich in gas and dust and are sites of vigorous star formation, but they lack the grand, symmetric design of a mature spiral. Irregular galaxies remind us that the process of galactic evolution is messy and ongoing. They represent the raw, unorganized building blocks of the universe, or the temporary, disrupted states that galaxies pass through on their way to a more settled form. The most dramatic evidence for this ongoing evolution comes from images that capture galaxies in the act of transforming each other. When two galaxies pass close by, their mutual gravity can create breathtaking visual spectacles. The antennae galaxies are a stunning example of such an interaction. In deep images, we see two distinct spiral galaxies that have recently collided. Their galactic disks have passed through each other, but their immense gravitational fields have ripped long, streaming tails of stars and gas out into intergalactic space, resembling the antennae of an insect. At the same time, the collision has compressed the vast gas reservoirs within both galaxies, igniting a firestorm of new star formation, visible as brilliant blue knots and red glowing nebulae throughout the overlapping regions. This is not a destructive act in the traditional sense, it is a creative one. The collision is driving the rapid assembly of new star clusters and will eventually, over hundreds of millions of years, lead to the complete merger of the two spirals into a single, new entity, most likely a large elliptical galaxy. The image of the antennae galaxies is a single frame from a billion-year-long movie, a visual narrative that illustrates the most powerful mechanism of galactic change. This simple visual taxonomy, born from classifying shapes on a photographic plate, is therefore far more than a filing system for astronomers. It is a fundamental key to understanding the life cycle of galaxies. The Hubble tuning fork diagram is not a static chart but a dynamic map of possible evolutionary paths. A gas-rich irregular galaxy might settle into a graceful spiral. Two spirals can merge to form a giant elliptical. The shape of a galaxy is a snapshot of its current state, a reflection of its mass, its gas content, and its recent interactions. By learning to read these shapes, we transform the night sky from a random collection of lights into a rich family album. Each galaxy portrait tells a story of birth, interaction, maturity, and sometimes a dramatic rebirth through collision. It reveals a universe that is not static, but a constantly evolving tapestry where gravity is the master weaver and light is the thread that tells the tale. But for all its grandeur, our Milky Way is not a solitary island in the great cosmic ocean. It is the anchor tenant of a small, gravitationally bound community known as the local group. This is our immediate galactic neighborhood, a collection of over 54 galaxies held together by their mutual gravitational pull, spanning a region of space about 10 million light-years across. Visualizing this group is the next step in understanding our cosmic address. The Milky Way and the Andromeda Galaxy are the two dominant spiral galaxies in this collection, comparable titans around which the rest of the local group orbits. Our galaxy is accompanied by an entourage of smaller satellite galaxies, the most famous being the Large and Small Magellanic Clouds, which are visible as faint, wispy patches in the southern hemisphere's night sky. On the other side, the Andromeda Galaxy, a faint smudge to the naked eye from a dark site, also has its own family of satellite galaxies, including the bright M32 and M110. Between these two giants lies the third largest member of the local group, the Triangulum Galaxy, or M33, a graceful face on spiral that may itself be a satellite of the colossal Andromeda. The rest of the group is composed of a myriad of tiny, faint dwarf galaxies, each a small, faint smudge of light that requires powerful telescopes to detect. A map of the local group would look less like a simple solar system and more like a bustling, three-dimensional archipelago, with two major islands surrounded by many smaller islets, all drifting through the void in a slow, gravitational dance that has been ongoing for billions of years. This dance, however, is leading to a dramatic climax. For nearly a century, astronomers have known that the Andromeda Galaxy is hurtling towards us. By carefully measuring the subtle redshift or blueshift of its light, we can determine its velocity with incredible precision. The conclusion is inescapable. In about 4.5 billion years, the Milky Way and Andromeda will collide. This is not a prediction of doom, but a forecast of a spectacular transformation. Artists' impressions and sophisticated computer simulations, based entirely on these precise velocity measurements and our understanding of gravity, allow us to visualize this future event. The initial approach will be a breathtaking sight in the night sky, with Andromeda growing from a faint smudge into a magnificent, full-fledged spiral. As the galaxies draw nearer, their mutual gravity will begin to warp their structures, pulling out long, streaming tails of stars, gas, and dust. The galaxies will then pass through each other, but because the spaces between stars are so vast, actual stellar collisions are exceedingly rare. Instead, the gravitational turmoil will trigger a massive burst of new star formation as clouds of gas are compressed. The skies of any planets within would be filled with brilliant new stars and glowing nebulae, a celestial firework display on a scale beyond comprehension. After this first pass, the galaxies will swing apart, only to be pulled back together by gravity, eventually merging into a single, new galaxy over the course of another 1 billion or 2 years. The end product of this cosmic merger will be an entirely new type of galaxy. The violent gravitational interaction will erase the elegant spiral structures of both the Milky Way and Andromeda. The ordered rotational motion of the stars will be randomized, and the remaining gas will be either used up in the starburst or blown away by the resulting radiation. What will remain is a vast, ellipsoidal swarm of stars, a giant elliptical galaxy. Astronomers have already nicknamed this future entity Milkomda. This visual narrative, from two distinct spirals to a single, featureless ellipse, is a powerful illustration of galactic evolution in action. It shows that galaxies are not permanent fixtures but dynamic entities that grow and change through collisions, a process that was much more common in the crowded early universe. The fact that we can predict and visualize this event so far in advance is a testament to the power of our physical laws and our ability to read the subtle clues written in the light of distant stars. When we zoom out even further beyond the confines of our local group, the universe reveals its true architecture on the grandest scale. Wide-field surveys, like the Sloan Digital Sky Survey, have mapped the positions of millions of galaxies, and the resulting visualizations are nothing short of astounding. The galaxies are not scattered randomly like sprinkles on a cupcake. Instead, they are arranged in an intricate, web-like pattern known as the cosmic web. This vast structure consists of great filaments or walls of galaxies that stretch for hundreds of millions of light years, intersecting at dense nodes where massive galaxy clusters reside. These filaments surround enormous, seemingly empty regions called voids, which can be hundreds of millions of light years across and contain very few galaxies. This sponge-like structure is one of the most important discoveries in modern cosmology. It is the large-scale structure of the universe, and it holds the key to understanding the forces that have shaped everything we see. These visual maps are not just pretty pictures, they are essential tools for probing the universe's greatest mysteries. The gravitational pull of normal matter alone is far too weak to have assembled this vast web in the 13.8 billion years since the Big Bang. The blueprint for this structure was imprinted in the tiny density fluctuations in the early universe, which we see as the temperature variations in the cosmic microwave background. But for those seeds to grow into the cosmic web we see today, there had to be an immense amount of invisible mass providing the gravitational scaffolding. This is the primary evidence for dark matter. The distribution of galaxies that we see visually traces out the underlying distribution of dark matter. The galaxies themselves are like lights on an invisible Christmas tree, marking the peaks of the dark matter density field. By studying the precise geometry of the filaments and voids, scientists can measure the properties of this dark matter, determining how sticky it is and how it clumps together over time. Furthermore, by measuring the distances and redshifts of galaxies at different depths, astronomers can create a three-dimensional map that also functions as a time machine. They can see how the cosmic web has evolved over billions of years. These observations have led to a second, even more profound discovery. The expansion of the universe is not slowing down due to gravity, as one might expect, but is actually accelerating. This acceleration is driven by a mysterious repulsive force dubbed dark energy. The visual evidence for this comes from seeing how the clustering of galaxies changes over cosmic time. The maps show that the cosmic web was growing more concentrated in the past, but the expansion driven by dark energy is now working against gravity, stretching the large-scale structure and making it slightly more diffuse over time. The visual tapestry of the cosmic web, therefore, is a dynamic battleground where the attractive force of dark matter and the repulsive force of dark energy are in a constant tug of war, shaping the fate of the entire universe. Ultimately, these visual journeys from our local group to the vast cosmic web provide the most profound context for our existence. They displace us from any notion of a central, privileged position. Our Milky Way is just one galaxy among 200 billion in the observable universe. Our local group is a typical small cluster, drifting on the outskirts of the Laniakea supercluster, which is itself just one of countless such structures in the cosmic web. We are not at the center of anything. We are residents of a modest galaxy in a modest group in an unremarkable filament of the grand cosmic tapestry. This realization is the ultimate expression of the Copernican principle. Yet, far from being diminishing, this perspective is empowering. It is a testament to our curiosity and ingenuity that from our tiny pale blue dot, we have been able to map our neighborhood, predict our future, and comprehend the architecture of the entire visible universe. The poetry lies in the scale itself, in our ability to use light to understand our true, humble, and magnificent place within the whole of creation. From the grand architecture of the cosmic web, we now turn to one of the most fleeting and mysterious signals in the universe, a cosmic shout that lasts less than the blink of an eye. These are fast radio bursts, or FRBs. For a few thousandths of a second, these events release more energy than our sun does in 80 years, all focused into a blistering flash of radio waves. The first one was discovered in 2007, buried in archival data from the Parkes Radio Telescope in Australia. It was so bright and so brief that for years, astronomers debated whether it was a genuine cosmic event or some local terrestrial interference, perhaps a microwave oven being opened prematurely at the observatory's facility. But as more telescopes began hunting for them, more of these bursts were found, confirming their origin far beyond our galaxy. They were arriving from deep intergalactic space, and their extreme intensity pointed to astrophysical processes of almost unimaginable power. The central mystery was profound. What natural engine could possibly produce such a short, sharp, and colossal release of energy? Since we cannot see FRBs with our eyes or optical telescopes, astronomers have had to develop a unique form of visual poetry to study them. The primary tool for capturing these ghosts is the dynamic spectrum. When a radio telescope detects a burst, it doesn't just record a simple blip. It measures how the intensity of the radio waves changes across a range of frequencies and over the incredibly short duration of the event. This data is then translated into a visual graph, a colorful and intricate fingerprint. Imagine a graph where time runs along the bottom and radio frequency runs up the side. The intensity of the signal is represented by color, often from blue for faint to red for intense. What appears for an FRB is a distinctive, slanted streak. This streak is not random. Its shape holds crucial information. The slant, a phenomenon called dispersion, occurs because lower-frequency radio waves travel slightly slower through the sparse electrons of intergalactic space than higher-frequency waves. The greater the delay, the more material the signal has passed through, allowing astronomers to estimate the vast distance the burst has traveled. The dynamic spectrum transforms an invisible, milliseconds-long event into a rich visual data set, a coded message that contains clues about its journey and its source. For the first decade of their study, all detected FRBs were one-off events. They flashed once from a random point in the sky and were never heard from again. This made them incredibly difficult to pinpoint. Without a repeat performance, it was nearly impossible to identify their host galaxy or understand what produced them. The major breakthrough came in 2016 with the detection of a repeating source, now known as FRB 121102. This changed everything. Instead of a single cryptic clue, astronomers now had a source that kept talking. This repetition allowed the world's most powerful radio telescopes, like the Arecibo Observatory and the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, to monitor its location and catch it in the act over and over again. With multiple bursts to study, astronomers could use a technique called interferometry to triangulate its position with exquisite precision. The repeating bursts were traced back to a small, faint, dwarf galaxy over 3 billion light-years away. This was a monumental step. It proved that at least some FRBs originate from persistent sources within specific galaxies, ruling out cataclysmic one-time events like the collision of two neutron stars for this class of burst. The mystery deepened, however, as different types of repeaters were found. Some, like FRB 121102, were incredibly active, firing off hundreds of bursts in a short period. Others were more sporadic. Then, in April of 2020, a truly game-changing event occurred. An extremely bright FRB was detected not from a distant galaxy, but from within our own Milky Way. Crucially, this burst was associated with a known object, a magnetar named SGR 1935+25. Magnetars are a special, ultramagnetic class of neutron stars, the collapsed cores of massive stars. They possess magnetic fields so powerful they could erase a credit card from a distance halfway to the moon. The simultaneous observation of an FRB from a known magnetar provided the smoking gun that directly linked at least one type of fast radio burst to these incredible stellar corpses. The visual data in this case was a multi-messenger masterpiece. While radio telescopes captured the burst itself, other space-based observatories detected a simultaneous giant flare of X-rays from the same magnetar. This connected the radio phenomenon to a known, if extreme, type of magnetar activity, where a starquake on the neutron star's incredibly rigid crust releases a torrent of energy, illuminating its surroundings with a pulse of radiation. Yet the story is far from complete. While magnetars explain some FRBs, particularly those within our galaxy, the immense power of the bursts coming from billions of light-years away suggests that even more extreme versions of these events, or entirely different mechanisms, must be at play in the distant universe. Could there be hypermagnetized magnetars, or are we seeing the result of cosmic collisions or the explosive evaporation of black holes? The dynamic spectra of these distant bursts remain the key visual puzzle. Their intricate structures, with multiple sub-bursts that sometimes drift downward in frequency like a cosmic slide whistle, challenge theorists to model the exact environment that could produce such complex signals. The visual data is both the question and the answer, a pattern of light on a graph that points to physics operating at the very edge of our understanding. Fast radio bursts represent the cutting edge of cosmic discovery, where a single, fleeting flash of radio waves, translated into a vivid visual signature, opens a window into the most energetic and enigmatic phenomena in the cosmos. The search for life beyond our planet has long been dominated by the act of listening, of tuning our radio telescopes to the silent frequencies of space, hoping to catch a deliberate hello. But what if another civilization is not broadcasting signals, but simply being? What if their presence is written not in radio waves, but in the light of their star, visible to anyone who knows how to look? This is the visual dimension of the search for extraterrestrial intelligence, a hunt for cosmic archaeology on a galactic scale, where we search not for a message, but for the fingerprints of a civilization so advanced its engineering has become visible across the interstellar void. The most compelling of these cosmic fingerprints is the concept of a Dyson sphere, proposed by physicist Freeman Dyson in the 1960s. The premise is rooted in energy consumption. Any civilization approaching our level of technological development would, theoretically, see its energy needs grow exponentially. The most abundant power source in any solar system is its central star. A highly advanced civilization might eventually learn to capture that star's entire energy output. They wouldn't build a solid shell. That's a science fiction simplification, but rather a vast swarm of orbiting energy-collecting satellites, a Dyson swarm that would encircle the star. While these collectors would absorb the star's visible light, they would also, according to the laws of thermodynamics, re-radiate that energy as waste heat in the form of infrared radiation. So, while the star might appear unusually dim or even dark in visible light, it would glow brightly in the infrared. To our telescopes, such a star would present a bizarre and unmistakable signature, an object with very little visible light but an enormous, unexpected infrared excess. Surveys from infrared space telescopes like NASA's Wide-Field Infrared Survey Explorer, or WISE, have actually searched for such anomalies. While they have found many strange objects, none have yet provided a clear, unambiguous signature of a Dyson sphere. But the search continues, scanning millions of stars for that telltale infrared glow of a civilization that has learned to harness the power of a sun. This theoretical search became thrillingly tangible with the strange case of Tabby's star, officially known as KIC 8462852. Discovered by citizen scientists as part of the Planet Hunters project using data from the Kepler Space Telescope, this star immediately stood out as bizarre. Planets transiting a star cause regular, symmetrical, and relatively small dips in its brightness, typically less than 1%. Tabby's star was different. Its light curve showed dramatic, irregular dimming events. Some dips were shallow, others were precipitous, blocking up to 22% of the star's light. Most startlingly, these dips were not periodic. They did not repeat on a regular schedule like a planet's orbit. This was not the signature of a planet, or even a family of planets. The scale and irregularity of the dimming were unprecedented. In the absence of a clear natural explanation, the hypothesis of alien megastructures entered the scientific discussion. Could we be seeing the transit of a partially built Dyson swarm, with its uneven structure causing the strange, aperiodic dips in light? It was a sensational idea, and it catapulted this obscure star into the global spotlight. What followed was a masterclass in how modern science investigates extraordinary claims. The alien megastructure hypothesis was not dismissed out of hand. It was treated as a serious, testable idea. Astronomers around the world turned a battery of telescopes toward Tabby's star, collecting new visual and spectroscopic data across the entire electromagnetic spectrum. This deeper look provided the answers. When the star dimmed, it did not dim equally at all wavelengths. The dimming was more pronounced in blue light than in red light. This is a crucial clue. A solid object like an alien megastructure would block all wavelengths of light equally. The wavelength-dependent dimming pointed instead to something made of small particles, dust. Further observations revealed that the star was also fading slowly over years, a trend inconsistent with a single, stable megastructure. The most likely explanation, supported by a wealth of subsequent data, is that Tabby's star is surrounded by a vast, uneven cloud of dust, possibly the remnants of a shattered moon or a collision between planetary bodies. This dust cloud, with its clumps and swirls, transits the star in an irregular pattern, causing the bizarre light curve. Yet, the story of Tabby's star is anything but a failure for SETI. It is a powerful success story. It demonstrated that our instruments are sensitive enough to detect anomalies that could, in theory, be signatures of astroengineering. More importantly, it showed that the scientific method is robust enough to investigate such claims rigorously. The initial hypothesis sparked a global observational campaign that ultimately revealed a fascinating, albeit natural, astrophysical phenomenon. The process transformed a mystery into a deeper understanding of planetary system evolution. It proved that unusual visual data can act as a powerful catalyst for scientific inquiry, pushing our observational capabilities to their limits in the pursuit of the universe's biggest questions. The search for extraterrestrial intelligence, therefore, is not a separate fringe activity. It is integrated into the very fabric of astronomy, a natural extension of our curiosity that asks, when we see something strange in the data, could this be it? The discovery of life beyond Earth, if it ever comes, may not arrive as a decipherable radio message. It may come first as a strange, anomalous squiggle on a light curve or an inexplicable infrared signature around a distant sun, a visual clue that prompts us to look closer, to question our assumptions, and to recognize that the universe's greatest mysteries are often hidden in plain sight, waiting for us to develop the eyes to see them. But when you download a stunning image from the Hubble Space Telescope's website, are you seeing what you would actually see if you were floating in space nearby? The answer is both yes and no, and understanding the distinction unlocks a deeper appreciation for these cosmic masterpieces. The process begins with a reality that might surprise you. Most telescopes, even the most powerful ones, do not capture color photographs in the way your smartphone does. Instead, they are essentially super-powered grayscale cameras. They collect light, but they do so through specific filters that act like incredibly precise color sieves. A telescope might be programmed to take one exposure through a filter that only allows a very specific shade of red light to pass through, corresponding to the glow of hydrogen gas. Then it will take another identical exposure through a filter for a specific green light, often linked to oxygen, and another for a blue wavelength, perhaps from sulfur or starlight. Each of these individual exposures is a black and white image, a map of where that particular type of light is strongest or weakest in the object. Creating what we call a true color image from this raw data is a meticulous process of translation and recombination. Astronomers take these three separate grayscale images, the red filter exposure, the green filter exposure, and the blue filter exposure, and assign them to the corresponding red, green, and blue channels of a digital color image. When these layers are combined, they blend together to create a full color picture that approximates what the human eye might perceive if it were sensitive enough to see these faint nebulae from space. The colors in a true color image are therefore a best effort reconstruction. They are grounded in the actual visible light emitted by the object, but they are often enhanced. The light from distant galaxies and nebulae is so faint that our eyes, which use rod cells for low light vision, would mostly see them in shades of gray. The process of combining the filtered exposures brings out the color that is physically present but too subtle for our biological hardware to register directly. This gives us a more vibrant, yet still representative, view of the cosmos as it would appear if our vision were as powerful as our telescopes. However, the universe is broadcasting in a spectrum of light far wider than the narrow slice our eyes can detect. This is where the equally important and often misunderstood technique of false color imaging comes into play. Think of it not as a deception, but as a necessary form of sensory translation. When a telescope like the Chandra X-ray Observatory observes a supernova remnant, it is capturing light that is fundamentally invisible to us. There is no true color for an X-ray because our eyes have no receptors for it. Similarly, the James Webb Space Telescope's primary view of the universe is in the infrared, the realm of heat. To make this hidden universe comprehensible, scientists assign visible colors to these invisible wavelengths. They might decide that the highest energy X-rays will be represented as blue, medium energy X-rays as green, and lower energy X-rays as red. The resulting image is a map, a visual key that allows our brains to intuitively understand the structure, temperature, and composition of the object. We can see at a glance where the most energetic processes are occurring versus the quieter regions. The iconic pillars of creation provides a perfect case study for how these different color schemes tell different scientific stories. Hubble has imaged this same region multiple times, each time with a different set of filters to answer different questions. The famous 1995 image, often described in true color terms, uses filters for hydrogen alpha, oxygen, and sulfur. The resulting picture, with its ethereal blue hues and fiery red pillars, is breathtaking and does approximate the visible light view. However, a more recent Hubble image of the same pillars used a broader set of filters, including light from nitrogen and hydrogen as well. This version reveals a much more complex structure, with a haunting magenta glow and intricate details not seen in the original. It is still based on visible light, but the choice of color mapping highlights different chemical elements, telling a richer story about the composition of the gas. Then, when James Webb turned its infrared gaze to the pillars, it created a completely different yet equally valid portrait. In Webb's view, the once opaque pillars become semi-transparent, their dusty veils nearly disappearing to reveal countless newborn stars within and behind them. The colors in Webb's image are assigned to specific infrared wavelengths, showing the distribution of dust and molecular hydrogen in a way that is impossible for Hubble to see. None of these images are the real pillars of creation. They are all real, they are just answering different questions. One shows us what we might see, while the others show us what is actually there, but hidden from our natural senses. This practice of color translation is fundamental to the progress of modern astronomy. It is how we take abstract columns of numbers and wavelengths and transform them into intuitive visual information that our pattern-seeking brains can analyze and understand. A false color image of a galaxy cluster that combines optical, X-ray, and radio data is not just a pretty picture, it is a diagnostic tool. The optical light shows the stars, the X-ray glow reveals the location of superheated gas, and the radio data might pinpoint the jets from a central black hole. By layering these datasets with color, a scientist can immediately grasp the relationships between these different components. It allows them to see how the invisible hand of dark matter, inferred from gravitational lensing, distorts the galaxies we can see. This is not artistic license in the way a painter might take liberties with a landscape. It is a rigorous, data-driven process of visualization. The colors are chosen not for their aesthetic appeal alone, but for their ability to communicate specific scientific information clearly and accurately. Therefore, the next time you marvel at a deep space image, you can appreciate it on two levels. On one hand, it is a work of profound art, designed to evoke a sense of wonder and to connect us emotionally to the vast cosmos. The choice of color palettes, even in false color images, is often made with an eye for beauty to engage the public and share the excitement of discovery. On the other hand, it is a dense package of scientific data, a visual representation of physical processes that can be measured and analyzed. understanding that these images are translations empowers you to become a more critical and informed observer. You can look at a brilliant blue and gold image from the James Webb Telescope and know that you are not looking at a faulty photograph, but at a map of chemical elements and physical conditions. You are seeing the universe through a sophisticated set of technological senses, each color a word in a language that describes the composition, temperature, and energy of the cosmos. This fusion of art and science is what makes astronomical imagery so powerful. It is a language that speaks both to our sense of wonder and our thirst for knowledge, translating the cold data of the universe into a visual poetry that everyone can understand. This collaborative spirit of discovery, of turning data into understanding, is not confined to professional scientists alone. In fact, the next great cosmic discovery could be made by anyone with an internet connection. This incredible translation of cosmic data into visual form has done more than just advance professional science. It has thrown open the doors of discovery to the entire world. We are living in an era of data deluge, where space telescopes and interplanetary rovers produce far more images and measurements than any single team of researchers could possibly analyze. This overflow of information has given rise to a powerful new force in astronomy. The citizen scientist, ordinary people from students to retirees, are now rolling up their sleeves and becoming cosmic image analysts, contributing directly to our understanding of the universe from their own homes. One of the most successful examples of this collaborative spirit is the Planet Hunters project. For years, NASA's Kepler Space Telescope stared unblinkingly at a single patch of sky, monitoring the brightness of over 150,000 stars, searching for the telltale dips caused by orbiting planets. The data it collected was immense, a river of light curves, graphs of a star's brightness over time, that needed to be sifted through. While computers are excellent at finding obvious, repeating patterns, they can sometimes miss the unusual, the messy, or the unexpected. The human brain, with its remarkable talent for pattern recognition, is perfectly suited for this task. On the Planet Hunters website, volunteers are presented with the light curve of a random star and asked a simple question: does this look like a planet's transit? They look for the characteristic U-shaped dip, but they are also on the lookout for strange asymmetries, multiple dips close together, or any anomaly that might defy a simple explanation. This collective human effort has been stunningly effective. Volunteers have identified numerous planet candidates that computer algorithms had overlooked, including some in the habitable zones of their stars, and even bizarre systems with multiple planets in highly unusual orbits. These discoveries are not just credited to a faceless institution, they are credited to the people who found them, turning abstract data into a personal triumph of discovery. The spirit of cosmic exploration extends far beyond the search for exoplanets, reaching all the way to the dusty surface of Mars. Every day, rovers like Curiosity and Perseverance beam back hundreds of images, creating a vast and growing photographic archive of the red planet. Scientists simply don't have the time to scrutinize every single rock, pebble, and distant hillside in every image. This is where projects like NASA, AI-4 Mars, and the Zooniverse platform's Planet 4 terrains come in. Volunteers are invited to log on and help classify the Martian landscape. They might be asked to outline interesting rocks, mark the boundaries of wind-blown sand dunes, or identify areas of potentially unstable terrain that could pose a risk to a rover's wheels. This isn't just busy work, it's crucial for mission planning and scientific targeting. But sometimes a volunteer's sharp eye catches something truly extraordinary. Anomalies that might have been scrolled past by a busy researcher can be flagged by a curious member of the public. unusual rock formations that could be geological oddities, or even dark, linear features that spark discussions about potential seasonal flows, have all been first spotted by citizen scientists. These observations don't always lead to paradigm-shifting discoveries, but they generate hypotheses. They point professional scientists toward targets of interest, ensuring that our robotic explorers are investigating the most promising and puzzling features. It is a perfect partnership between human curiosity and robotic capability. What makes this global collaboration possible is the inherently visual nature of the data. You don't need a PhD in astrophysics to recognize a dip in a graph or a strange-shaped rock. The language of these images is intuitive. A swirling galaxy, a cratered planet, a wiggling line on a graph, these are patterns we are wired to understand. This accessibility is what democratizes science. It breaks down the barriers between the ivory tower and the public square, proving that the poetry of space is not written in an arcane code for experts alone. It is a narrative that anyone can learn to read, and in doing so, become a co-author of the story. This collective effort transforms the exploration of cosmic mysteries from a solitary pursuit into a truly human endeavor. A global community united by a shared sense of wonder and a desire to understand our place in the cosmos. It proves that the drive to explore is a fundamental part of who we are, and that in the age of information, a single curious person, looking closely at an image from a world millions of miles away, can still make a difference. This incredible democratization of cosmic discovery, where anyone can help analyze data from Mars or distant stars, finds its most personal and artistic expression in a pursuit that turns our own backyards into portals to the universe. Astrophotography is the art of capturing light that has traveled for thousands or even millions of years, using equipment that is increasingly accessible. It is a discipline where patience and passion can produce images of nebulae and galaxies that, just a generation ago, were only possible for the world's largest professional observatories. This is not about simply pointing a camera at the sky. It is a sophisticated dance with technology and nature, a process of coaxing faint details from the glow of light pollution and the turbulence of our own atmosphere. The fundamental challenge every astrophotographer faces is signal versus noise. The light from a distant galaxy is incredibly faint, a whisper of photons arriving at our cameras. Meanwhile, the camera's sensor itself generates random electronic noise, and the bright sky glow from city lights adds a pervasive, unwanted signal that can easily drown out the celestial target. The solution is a technique called image stacking. Instead of taking one long, several-hour exposure which would be ruined by a passing satellite, a gust of wind shaking the telescope, or the inherent noise, astrophotographers take hundreds, sometimes thousands, of individual short exposure images. Each of these frames or sub-exposures might be only 30 seconds to a few minutes long. Individually, they look like a grainy, murky mess with the target object barely visible. But then, using specialized software, these frames are precisely aligned and stacked on top of one another. In this process, the random noise averages out, canceling itself, while the consistent signal from the galaxy or nebula adds up, becoming stronger and clearer with each new frame added to the stack. It is a mathematical miracle of persistence, transforming a chaotic soup of data into a crisp, deep portrait of the cosmos. This is often combined with other frames called darks, flats, and bias frames, which calibrate out imperfections in the camera sensor and optical system, a meticulous process that reveals the true beauty hidden within the data. The techniques vary dramatically depending on the subject, each requiring a different approach and showcasing a different facet of the sky's visual poetry. For capturing the grand sweep of the Milky Way arching across a dark sky, A wide-angle lens on a sturdy tripod is enough. Here, the art is in the time-lapse, where a sequence of images taken over hours is combined into a video that shows the Earth's rotation, with the stars tracing perfect concentric circles around the celestial pole. It is a visceral reminder that we are on a spinning planet, a cosmic carousel ride that we can witness from our own backyards. On the other end of the spectrum lies planetary imaging. Here, the goal is not to collect faint light but to capture fine detail on small, bright objects like Jupiter, Saturn, or Mars. This battle is fought against the Earth's atmosphere. The constant churning of air cells blurs and distorts the view, making a planet appear to boil and shimmer. The key is to capture moments of exceptional stability, known as good seeing. Astrophotographers use high-speed cameras to take thousands of frames in a matter of minutes, creating a video of the planet. Specialized software then analyzes each frame, ranks them for sharpness, and combines only the clearest few percent into a final, stunningly detailed image. This is how amateurs capture the cloud bands on Jupiter, the Cassini division in Saturn's rings, and the ice caps on Mars with a clarity that would have amazed professional astronomers a few decades ago. But perhaps the most transformative aspect of astrophotography is the deeply personal connection it forges. This is not a passive act of looking at an image produced by a space agency. It is an active, immersive experience. It involves spending cold, clear nights under the stars, learning the constellations, and guiding a telescope to a faint smudge in the sky that a chart says is the Andromeda galaxy. There is a profound moment of realization when that faint smudge, after hours of work capturing and processing data, resolves into a spiral galaxy of stars, our island universe 2.5 million light-years away, rendered by your own effort. The process itself becomes a form of meditation and a technical craft, blending art with science. The final image is more than a photograph. It is a personal trophy, a testament to patience and skill, and a unique artistic interpretation of a universal subject. No two astrophotographs of the same nebula are ever exactly alike, as each photographer brings their own choices in color balance, composition, and processing to create their own version of the cosmic poetry. This pursuit powerfully demonstrates that the wonder of the universe is not the exclusive domain of billion-dollar telescopes in space or on remote mountaintops. While those instruments push the boundaries of science, the emotional and aesthetic resonance of the cosmos is available to anyone with a camera, a telescope, and the willingness to look up. Astrophotography fosters a deep, intimate connection to the mysteries above. It makes the cosmos a familiar place, not a distant abstraction. The amateur, working from a suburban driveway, can produce an image of a dying star's nebula that inspires the same awe as a Hubble portrait because it is their own. It is a direct, hands-on engagement with the light of the universe, a hobby that turns observers into participants in the great human endeavor of cosmic exploration, proving that the sky above is a canvas waiting for every one of us to paint our own interpretation. This journey through the cosmos, from the violent hearts of distant galaxies to the silent plains of Mars, ultimately brings us back to a profound reflection on ourselves. While we have been exploring how imagery deciphers the universe's physical secrets, its most powerful impact might be on the human psyche. There is a name for this transformative experience, one described by those few who have witnessed our world from the void, the overview effect. Astronauts who have traveled to the moon and gazed back at the Earth consistently report a cognitive shift that is difficult to put into words. They speak of the planet not as a map with borders and nations, but as a single, vibrant, and breathtakingly fragile oasis. The endless political conflicts, the economic divisions, the artificial boundaries that define our daily lives, all of it seems to vanish, replaced by an overwhelming sense of global interconnectedness and a deep, personal responsibility for this tiny, precious marble of life suspended in the blackness. It is a visceral understanding that our atmosphere is nothing more than a thin, shimmering glaze, the only thing protecting everything we know and love from the cosmic vacuum. Very few of us will ever have the privilege of seeing Earth from orbit, but we do not have to leave the ground to feel a whisper of this perspective shift. This is the unique power of certain space images. They act as proxies for the astronaut's experience, delivering a dose of the overview effect directly to our consciousness. The first and perhaps most pivotal of these icons was captured on Christmas Eve 1968 by the crew of Apollo 8. As their spacecraft emerged from behind the moon, the astronauts witnessed something no human eyes had ever seen: Earthrise. The photograph they took shows our world, a brilliant swirl of blue and white, rising over the barren, desolate horizon of the moon. The contrast could not be more stark. The moon is a testament to cosmic stillness and desolation, a world of stark grays and lifeless craters, and there, hanging in the black sky above it, is Earth, a vibrant, dynamic, and unmistakably alive world. This single image reframed our entire existence. It presented Earth not as a limitless resource to be exploited, but as a singular, beautiful, and isolated system. It was the first time we saw our home as a whole, and the effect was immediate and profound. That sense of global identity was solidified just a few years later by another iconic view, the blue marble. Taken by the crew of Apollo 17 on their way to the moon, this photograph is arguably the most distributed image in human history. It shows the planet fully illuminated, with the entire African continent visible, swirled by bright white clouds and set against the deep blue of the oceans. There are no national borders visible from this distance. The image presents a unified whole, a complex biosphere that we all share. The blue marble did not just inspire awe, it became a catalyst for a burgeoning global consciousness, particularly the environmental movement. For the first time, the phrase "Spaceship Earth" felt viscerally real. We could see that we are all crew members on this vessel, sharing a finite supply of air, water, and land. The image became a powerful symbol for the first Earth Day, and has been used ever since to advocate for international cooperation on issues like climate change and conservation. It visually demonstrates that environmental problems do not respect political lines. They are challenges that face all of humanity equally. This ability of a single visual to alter our collective perspective on a mass scale is a testament to the deeper power of cosmic imagery. It moves beyond pure science and into the realm of philosophy and ethics. The visual poetry of space does more than answer how stars are born or how galaxies evolve. It forces us to confront the questions of why we are here and what our role should be. When we see the pale blue dot, a single pixel in a vast sunbeam, it instills a profound sense of humility. Our individual concerns, our tribal squabbles, our entire history has played out on that speck. This perspective is not meant to diminish our significance, but to redefine it. Our importance lies not in our domination of the planet, but in our ability to recognize our shared predicament and our collective responsibility as stewards of this rare and fragile world. The images from space provide a common reference point for all of humanity, a shared vision of home that can, if we let it, unite us across cultures and ideologies. Therefore, the cameras on our telescopes and spacecraft are not merely scientific instruments, they are also mirrors. They show us the grandeur of the cosmos, but in doing so, they reflect back an image of ourselves that is both humbling and empowering. They reveal that the greatest mystery may not be hidden in a distant nebula or a black hole's shadow, but in our own capacity for wisdom, for cooperation, and for compassion. The visual poetry of space, at its most profound, challenges us to grow up as a species, to match the breathtaking scale of the universe we are discovering with an equally expansive sense of care for our only home and for each other. It suggests that the ultimate destination of our cosmic journey is not a place out there among the stars, but a new state of awareness right here on Earth. The journey of cosmic imaging has been one of constant revolution, from Galileo's sketches to Webb's deep field revelations. But what we have witnessed so far may be merely the overture to a far grander symphony of discovery. The next generation of observatories, already under construction or in advanced planning, promises to transform our visual understanding of the universe once again, not by just seeing deeper, but by seeing everything, everywhere, all at once. This new era will be defined by a shift from studying individual cosmic objects to comprehending the universe as a dynamic, evolving system. And the flagship of this movement is an observatory that will turn the static sky into a breathtaking cosmic movie. Scheduled to begin its operations in the next few years, the Vera C. Rubin Observatory in Chile represents a fundamental change in how we observe the cosmos. Its primary instrument, the Legacy Survey of Space and Time camera, is a technological marvel unlike any other. With a resolution of 3.2 gigapixels, it would take over 1,500 high-definition television screens to display just one of its full images. But its true power lies not in a single snapshot, but in its relentless pace. Every few nights, this behemoth will capture a complete panorama of the entire southern sky. It will then do it again and again, night after night, for an entire decade. This will not produce a collection of pretty pictures. It will generate a petabyte-scale time-lapse movie of the universe. By comparing each night's scan with the previous one, Rubin's powerful computers will flag anything that has changed, moved, or appeared. This dynamic vision will allow it to detect millions of transient events, supernova exploding in real time, asteroids whizzing through our solar system, and stars flaring unexpectedly. It is expected to increase the number of known objects in our solar system by a factor of 10, mapping the outer reaches with unprecedented clarity. But its most exciting discoveries will likely be the ones we cannot yet predict, the strange, unexplained flashes and movements that will challenge our current models and undoubtedly reveal entirely new classes of celestial phenomena. While the Rubin Observatory will provide the wide-angle, all-sky view, the Nancy Grace Roman Space Telescope, named for NASA, a first chief astronomer, will act as Hubble's wide-field successor, combining the sharpness of a space-based observatory with a field of view 100 times larger than Hubble's. Imagine trying to study the ecology of a forest by looking through a soda straw. That has been the challenge with many powerful telescopes, which see deeply but only in tiny patches. The Roman Space Telescope will throw open the windows. It will be able to capture vast swaths of the sky with Hubble-like clarity in a single observation. This extraordinary capability is perfectly suited for tackling two of the biggest mysteries in cosmology, dark energy and exoplanets. To understand why the universe's expansion is accelerating, Roman will perform gigantic surveys of the sky, measuring the distances and distributions of millions of galaxies across cosmic time. This will allow scientists to map the influence of dark energy with unprecedented precision, tracing how its repulsive force has shaped the large-scale structure of the universe over billions of years. In the realm of exoplanets, Roman will use its wide field to conduct a sophisticated microlensing survey. It will monitor hundreds of millions of stars at the crowded center of our galaxy, watching for the subtle brightening that occurs when an unseen planet's gravity bends the light of a background star. This technique is especially sensitive to planets in the cold, outer regions of their star systems, including free-floating rogue planets drifting alone in the dark. Roman will give us a statistical census of planets throughout the galaxy, answering the question of how common solar systems like our own truly are. Yet, even these monumental projects are not the final horizon. Astronomers are already dreaming of concepts that sound like science fiction, but are grounded in the firm principles of physics. One of the most ambitious is the idea of using the Sun itself as a gravitational lens telescope. Einstein's theory of general relativity tells us that a massive object like the Sun bends light, acting as a lens. The focal point for this lens, however, is not close to the Sun. It is incredibly far away, far beyond the orbit of Pluto. If we could send a spacecraft to this distant point, roughly 550 astronomical units from the Sun, we could, in theory, achieve resolution power beyond imagination. Such a telescope could potentially resolve the surface features of an exoplanet in another star system, seeing continents and clouds on a world light years away. The engineering challenges are staggering. The spacecraft would have to travel further than any human-made object has ever gone, and maintaining precise alignment over such vast distances would be extraordinarily difficult. But the scientific payoff would be revolutionary, turning distant points of light into detailed, mapped worlds and potentially allowing us to search for direct signs of life. These future instruments, from the relentless sky mapper Rubin to the wide-eyed Roman and the visionary solar lens telescope, all share a common promise. They will not merely provide answers to the questions we are asking today about dark energy, exoplanets, and cosmic evolution. Their greatest gift will be the new questions they force us to ask. Every time we have built a new window on the universe, we have been humbled by discoveries we never anticipated. The Hubble Deep Field revealed a universe teeming with galaxies where we expected emptiness. The detection of gravitational waves opened an entirely new sense with which to perceive the cosmos. The next generation of telescopes will undoubtedly do the same, presenting us with anomalies, paradoxes, and wonders that will challenge our fundamental understanding of physics and our place in the cosmos. The future of cosmic imaging is not just about sharper pictures. It is about writing the next chapter in a story that is forever expanding, filled with mysteries we have not yet even learned how to imagine. Yet, for all the apparent objectivity of our telescopes, the universe we see is not a raw, unfiltered reality. It is a curated gallery, a carefully selected portfolio shaped by a complex set of human decisions. Behind every breathtaking image lies a fundamental and often overlooked question. With a whole sky full of wonders, how do we choose what to see? The process of allocating precious telescope time, especially on flagship observatories like Hubble or James Webb, is a delicate and fiercely competitive endeavor, one where scientific merit must be balanced against public engagement and where aesthetic beauty often quietly guides the lens. The most formal pathway is through a proposal system. Thousands of astronomers from around the world submit detailed arguments, making their case for why a specific target deserves hours or even days of a multi-billion-dollar observatory's life. These proposals are subjected to a rigorous peer review process where committees of experts weigh the potential scientific return. A project aiming to study the atmospheric composition of a potentially habitable exoplanet will likely be prioritized over a project to take a prettier picture of a well-known nebula. This system is designed to maximize discovery, to push the frontiers of knowledge in the most efficient way possible. It is a process driven by data, by hypothesis, and by the relentless pursuit of answering fundamental questions about dark matter, galactic evolution, or the origins of life. However, scientific priority is not the only factor at play. A small but significant portion of observation time on major telescopes is reserved at the discretion of the Institute's director. This discretionary time is often used for targets that have a high potential for public impact. This is where the less tangible but equally powerful force of aesthetic beauty and public appeal enters the equation. The most famous example is the Hubble Space Telescope's revisit to the pillars of creation in the Eagle Nebula. The original 1995 image was a cultural sensation, adorning posters, album covers, and inspiring an entire generation. When Hubble's new, more advanced camera was installed, scientists chose to point it at the pillars once more. The resulting 2014 image was sharper, wider, and more detailed, but the core scientific justification was arguably secondary. The primary motivation was to capture an icon in a new light, to rekindle public wonder, and to demonstrate the continued power of the telescope. This was not a decision based on a new hypothesis about star formation, but on a recognition that some images transcend pure data. They become touchstones for our relationship with the cosmos, and maintaining that connection is a vital part of the scientific mission itself. This curation extends beyond the initial click of the shutter to the very way images are processed and presented to the world. Once the raw, grayscale data is collected through various filters, a team of imaging specialists, often in collaboration with the scientists, must decide how to translate it into a color picture. This is where a subtle ethical dimension emerges. Should the final image be optimized for scientific clarity, where the color choices are made purely to highlight specific chemical elements or physical structures, even if the result appears unnatural to the public eye? Or should it be processed for public wonder, where the colors are balanced to create a visually stunning and emotionally resonant image that faithfully represents the scene but prioritizes aesthetic impact? There is no single correct answer. An image intended for a research paper might use a high-contrast, false color scheme that makes a faint jet from a black hole pop, while the press release image of the same data might use a softer, more natural-looking palette to evoke a sense of serene beauty. This is not a deception, but a form of translation tailored for different audiences. The ethics lie in the transparency of the process. Reputable institutions like NASA and ESA are careful to label their images, explaining which are natural color approximations and which are false color representations used to convey specific scientific information. Ultimately, this meta-discussion reveals a profound truth about the visual poetry of space. The cosmos we see through our telescopes is not a passive reality that simply imprints itself upon our senses. It is an active construction, a collaborative artwork created by scientists, engineers, and image processors. The choices of what to look at, for how long, and how to present the findings are all shaped by human values, priorities, and even our innate sense of beauty. Understanding this curation does not diminish the images, it enriches them. It adds a layer of depth, reminding us that these portraits are part of a conversation between humanity and the universe. They are not just pictures of the cosmos, they are pictures of our relationship with the cosmos, reflecting not only the physical laws of nature, but also our enduring desire to find meaning, order, and breathtaking beauty in the great expanse. This realization invites us to be more critical and appreciative viewers, to see the images not as absolute truths, but as carefully crafted stories that blend hard data with human wonder. We have journeyed across the cosmos through the lens of our most powerful instruments, witnessing the birth of stars and the dance of galaxies. We have translated invisible light into breathtaking vistas and felt the vibrations of space-time itself. Yet, for all this astonishing progress, our visual exploration inevitably brings us to a precipice, a boundary beyond which our cameras, no matter how advanced, simply cannot see. There are fundamental mysteries in the universe that may forever resist being captured in any form of picture, not due to a lack of technological ingenuity, but because of the very nature of reality itself. Consider the ultimate cosmic vault, the interior of a black hole. We have triumphed in photographing its shadow, the dark silhouette cast by the event horizon against the glowing accretion disk. But that horizon is a point of no return, a one-way door in the fabric of space-time. What lies inside is, by definition, hidden from our universe. The laws of physics, as we understand them, break down at the singularity, the point of infinite density at the black hole's heart. No light, no information, no signal of any kind can escape to bring us a postcard from that realm. Any image we could possibly conceive of the interior is not a photograph but a mathematical speculation, a set of equations describing a place where space and time swap roles and our conventional understanding of cause and effect ceases to exist. It is a domain where visualization fails, and we are left with the pure, abstract language of general relativity and quantum mechanics to guide our imagination. This challenge extends to the very beginning of everything. The cosmic microwave background gives us a baby picture of the universe when it was 380,000 years old. But what about the moment of the Big Bang itself, or the state of the universe in the first incomprehensibly tiny fraction of a second? The conditions were so extreme that the universe was opaque, a searing, dense plasma where the very concept of looking has no meaning. And what, if anything, came before the Big Bang? The word before may itself be meaningless if time as we know it began with that event. Was there a previous universe that collapsed? Are we part of a cyclical cosmos or one bubble in a vast, frothing multiverse? These are not questions that can be answered by building a bigger telescope. They are questions that live in the realm of theoretical physics, where concepts like cosmic inflation, higher dimensions, and the quantum birth of spacetime are explored through complex mathematics. There is no possible image of the multiverse, no photograph of a colliding brain or an inflating false vacuum. These ideas are tested not by direct observation, but by the subtle fingerprints they might have left on the observable universe, like the specific pattern of the cosmic microwave background. This limitation is not a failure of science or a shortcoming of our curiosity. It is a profound reminder that the universe's deepest secrets may be encoded in a language beyond light. For centuries, our primary sense for exploring the cosmos has been sight, but the most fundamental truths about reality may not be visual at all. They may be mathematical, logical, or conceptual. The great physicist John Archibald Wheeler speculated that at its foundation, the universe might be based on information, a world of it from bit where particles and forces emerge from a substrate of pure data. How would you take a picture of that? The challenge, then, is to develop new ways of seeing that rely less on our eyes and more on our minds. We must learn to perceive the cosmos through the elegance of an equation, the consistency of a theory, and the power of abstract thought. This is where the visual poetry of space finds its most profound partner, pure mathematics. The journey that begins with a stunning Hubble image of a nebula ultimately leads us to the chalkboard, to the complex symbols that describe the quantum fields and gravitational waves that govern that nebula's evolution. The beauty of a spiral galaxy's arms finds a parallel in the beauty of the differential equations that describe its rotation. The edge of the knowable is not a barren wasteland. It is a frontier where our intuition, built from a human-scale world, must be supplemented by the rigorous logic of mathematics. Here, the poetry of the cosmos is written not in color and light, but in the universal language of geometry, symmetry, and number. Our visual journey thus completes a grand circle, reminding us that while images ignite our wonder and make the cosmos accessible, the final and most satisfying understanding may come from a source that can never be rendered in pixels, but only contemplated in the silent, profound language of the mind. But what if the poetry of the cosmos could be experienced not just with our eyes, but with our ears as well? We have spent this entire journey exploring how light is translated into images, but there is a growing movement to add a new dimension to our perception of the universe: sound. This innovative practice is called data sonification, and it involves converting the numerical data from telescopes and other instruments into audible frequencies, allowing us to literally hear the images we have been admiring. It's a process that turns the visual symphony of the cosmos into an actual one, revealing patterns and rhythms that our eyes might easily overlook. Think of it like a Geiger counter. The device doesn't show you a picture of radiation. It translates an invisible phenomenon into a series of clicks that your brain can immediately interpret. The faster the clicks, the more intense the radiation. Data sonification applies this same principle on a cosmic scale. For instance, consider the Perseus galaxy cluster, one of the most massive objects in the known universe. At its heart lies a supermassive black hole, and the immense gravitational energy it releases sends pressure waves rippling through the superheated gas that fills the cluster. The Chandra X-ray Observatory can image these waves as vast, subtle ripples in the gas like rings on a pond, but in 2023, scientists sonified this data. They assigned a note to the detected pressure waves, shifting the frequencies up by 57 and 58 octaves to bring them into the range of human hearing. The result is not a random noise, but a series of haunting, ethereal notes, a chord that has been propagating through space for 2.5 billion years, which we can now listen to. It is a black hole song, a direct auditory experience of one of the universe's most powerful phenomena. The process of sonification can be applied to any astronomical image, creating a soundscape that is as unique as a fingerprint. Take a picture of the center of our own Milky Way galaxy, a crowded, vibrant region teeming with stars and glowing clouds of gas. To sonify this, astronomers might scan the image from left to right. As the scan moves, the brightness of each pixel is mapped to a specific pitch and volume. A bright star might become a high, clear tone, while a dark cloud of dust would create a moment of silence or a low drone. The result is a sweeping auditory panorama. You would hear the central bulge of the galaxy as a dense cluster of high-pitched notes, while the sparser outer regions would produce a more scattered, lower-frequency sound. Different elements can be assigned different instruments. Hydrogen might sound like a string section, while X-ray data could be represented by percussive beats. This multi-layered approach allows researchers to perceive correlations or anomalies between different data sets in a completely new way. A feature that might be visually subtle could create a distinctive sound pattern that draws immediate attention. This multi-sensory approach is more than just a novelty. It is a powerful tool for discovery and accessibility. For scientists, listening to data can reveal subtle patterns that are difficult to spot in a visual graph or image. The human ear is exceptionally good at detecting rhythmic patterns, changes in tempo, and slight dissonances. A sonified light curve of a star might reveal a tiny, recurring dip caused by an orbiting planet that a visual scan could miss. But perhaps the most profound impact of sonification is its ability to make the wonders of astronomy accessible to the visually impaired. For the first time, a person who is blind can experience the structure of a nebula or the scale of a galaxy cluster through a rich, immersive soundscape. Projects like NASA, a universe of sound, are dedicated to creating these auditory experiences, democratizing access to cosmic discovery. and ensuring that the poetry of space is a language available to everyone, regardless of their ability to see. Ultimately, data sonification expands our very definition of what it means to observe the universe. It proves that the cosmos communicates not just through light, but through rhythm, pitch, and scale. It challenges the primacy of vision in science, reminding us that our other senses can offer equally valid pathways to understanding. By adding sound to our exploration toolkit, we are not replacing the image. We are composing a fuller, richer symphony of knowledge. The universe has always been vibrating with energy. We are only now learning how to tune in and listen to its deepest melodies, discovering that the same physical laws that create a spiral galaxy also have a distinct and beautiful musicality. The journey of cosmic imagery from a scientific tool to a cornerstone of our culture began in earnest with a single, powerful voice that understood its potential to stir the human soul. In 1980, astronomer Carl Sagan launched his television series, Cosmos, a personal voyage into the world, and in doing so, he fundamentally changed our relationship with the universe. Sagan's genius was in his use of visual storytelling. He didn't just present facts, he used the nascent technology of special effects and animation to take viewers on a journey. He stood on a metaphorical shore of the cosmic ocean, with a galaxy spinning behind him, and made the scale of space feel both awe-inspiring and intimately personal. The series was filled with what were then cutting-edge visualizations, the evolution of galaxies, the calendar of cosmic time, and the surfaces of alien worlds. But more than any single effect, it was Sagan's reverence for the images themselves that resonated. When he held up a photograph of Mars or described the pale blue dot, he was not just a scientist explaining data. He was a poet inviting us to see ourselves as part of a grand cosmic story. He used these visuals to instill what he called a sense of wonder, arguing that understanding the cosmos was not a cold, clinical exercise, but a deeply humanizing one. Cosmos reached hundreds of millions of people, creating a generation that looked at a picture of a nebula and saw not just gas and dust, but a nursery for stars and a testament to the creativity of nature. Sagan proved that space imagery could be a bridge, connecting the abstract world of astrophysics to the universal human emotions of curiosity, humility, and awe. That bridge, built by Sagan, has since been traversed by billions. The cultural vessel for this journey in the 21st century is social media, where Cosmos was a scheduled event, a weekly appointment with the universe. Platforms like Instagram, Twitter, and Facebook deliver the cosmos to our pockets in a continuous, breathtaking stream. The official accounts of NASA, the European Space Agency, and other space institutions have mastered the art of the cosmic reveal. A new image from the James Webb Space Telescope isn't just released in a dry scientific paper. It is unveiled in a carefully crafted social media post, often with a stunning video zooming into its intricate details, set to evocative music. These images go viral within minutes, shared and commented on by people from every corner of the globe. An amateur astrophotographer in a suburban backyard can capture a detailed portrait of the Andromeda galaxy and share it with a worldwide community of enthusiasts, receiving instant feedback and admiration. This constant, democratized flow of imagery has transformed the universe from a distant abstraction discussed by experts into a daily presence in our lives. We scroll past a video of a solar flare on the same feed where we see photos from friends and news headlines. The cosmos has been woven into the very fabric of our digital existence, making cosmic wonder a routine, accessible experience rather than a rare privilege. This daily immersion in cosmic beauty has, in turn, sparked a renaissance of artistic expression. the visual poetry of space is no longer confined to textbooks and documentaries. It has become a profound source of inspiration across every creative discipline. Digital artists use Hubble and Webb images as backdrops for fantastical scenes, blending scientific accuracy with imaginative storytelling. Musicians compose symphonies inspired by the movements of the planets or the eerie silence of the void, with albums structured around the life cycle of a star or the concept of cosmic inflation. Science fiction literature and film are now more visually authentic than ever, with directors and authors drawing directly on real imagery to craft their visions of interstellar travel and alien landscapes. The vibrant nebulae and stark Martian sunsets we see in blockbuster movies are often direct homages to the data beamed back by our telescopes and rovers. This artistic feedback loop is powerful. The images inspire art, and the art, in turn, deepens our emotional connection to the science, making the cosmos feel more relatable and stirring our imagination about what might be possible. Ultimately, this collective visual experience is forging a new kind of cultural heritage, one that transcends national borders, political divisions, and cultural differences. When a new deep-field image is released, it is celebrated and discussed by people in every country on Earth. There is no American galaxy or European nebula. There is only a shared cosmic vista that belongs to all of humanity. This common visual language reminds us of a fundamental truth that Sagan eloquently articulated, that we all live on a small world, a pale blue dot suspended in a sunbeam. In an era often defined by conflict and disagreement, the shared awe we feel for a photograph of Saturn's rings or the pillars of creation provides a rare and precious point of unity. It shapes a collective vision of a future where humanity is not confined to its planet of origin, but is a species with a destiny among the stars. The images become more than data. They are symbols of hope, curiosity, and our shared origins in the stardust of ancient suns. They are the visual foundation for a planetary identity, reminding us that before we are citizens of any nation, we are citizens of the cosmos. This cultural legacy, passed down from Sagan's ship of the imagination to the infinite scroll of social media, ensures that the visual poetry of space will continue to inspire, humble, and unite us for generations to come. To truly appreciate how a single astronomical image can hold an entire library of scientific history, let us focus our gaze on one of the most studied and iconic objects in the sky, the Crab Nebula. This wispy, ethereal cloud floating in the constellation Taurus is far more than a beautiful cosmic fossil. It is a crime scene, an ongoing physical laboratory, and a living timeline, all captured in a single frame. Its story begins not with a telescope but with ancient records. In the year 1054 AD, Chinese and Arab astronomers documented a new star in the sky, so brilliant it was visible in broad daylight for weeks. They were witnessing the violent death of a massive star, a supernova explosion, an event that left behind the expanding cloud of debris we see today. When we look at a modern image of the Crab Nebula, we are therefore looking directly at the aftermath of a cataclysm that was personally recorded by humans nearly 1,000 years ago. This immediate connection to our own history makes the crab a uniquely powerful subject, a bridge between ancient sky watchers and modern astrophysics. The most familiar portrait of the crab comes from the optical light captured by telescopes like Hubble. In this view, we see a chaotic web of glowing filaments, like a tangled skein of silk stretched across space. The colors in this image are not arbitrary, they are a direct chemical fingerprint. The dominant reddish-orange hue comes from ionized hydrogen gas, the primary constituent of the star's outer layers that were blasted into space. The delicate bluish filaments are the signature of neutral oxygen. This intricate structure is the expanding debris field from the explosion itself. The material is rushing outward at speeds of several million miles per hour, and the filaments are shaped by complex interactions between this outward blast wave and the slower moving material it collides with. But the optical view is just the beginning of the story. It shows us the aftermath, the expanding shell of the star's corpse, but it does not reveal the powerful engine that continues to energize the entire nebula, keeping it shining brightly a millennium after the initial blast. To find that engine, we must switch our vision to the high-energy world of X-rays, using an observatory like Chandra. The X-ray image of the Crab Nebula is stunningly different. The faint filamentary structure vanishes, replaced by a brilliant, ghostly glow that fills the nebula's center. This glow is not from hot gas, but from something far more exotic: synchrotron radiation. This is the light emitted by electrons spiraling at nearly the speed of light through powerful magnetic fields. At the very heart of this X-ray glow lies a tiny, pinpoint object, the Crab pulsar. This is the crushed core of the original star, a neutron star spinning 30 times every second. As it rotates, it acts like a colossal cosmic dynamo, generating an intense magnetic field and blasting out a wind of high-energy particles. This pulsar wind slams into the surrounding nebula, energizing it and causing it to glow across the electromagnetic spectrum. The Chandra image, therefore, reveals the beating heart of the Crab. It shows us the ongoing power source, the remnant of the star's core that is still driving the nebula's evolution long after the star's death. Now, let us add a third layer to our understanding by observing the Crab in the infrared with a telescope like Spitzer or James Webb. The infrared view highlights yet another component: cosmic dust. The explosion of a supernova is a crucible for element creation, forging heavy atoms like carbon, silicon, and iron. As the expanding cloud cools, these elements can condense into tiny solid particles, dust grains. The infrared image shows this dust glowing warmly, distributed throughout the nebula. This is a crucial piece of the cosmic recycling puzzle. The same cataclysm that destroyed a star also scattered the essential ingredients for future planets and life. The dust we see in the Crab Nebula will one day be incorporated into a new generation of stars and planetary systems. By comparing the distribution of dust in the infrared with the gas filaments in optical light and the energetic particle wind in X-rays, scientists can study how these different components interact, how the dust is destroyed or survives in the harsh environment created by the pulsar. The true power of modern astronomy lies in our ability to combine these different views into a single, coherent narrative, a composite image that layers the optical, X-ray, and infrared data is a multi-dimensional storybook. The red filaments tell the story of the star's death. The blue X-ray glow reveals the powerful activity of its reanimated core. The infrared dust shows the creation of the building blocks for new worlds. But the narrative does not stop with a static picture. Because we know the exact date of the explosion from historical records, we can measure the nebula's expansion rate with extraordinary precision. Time-lapse observations over years and decades show the filaments visibly moving outward, allowing us to rewind the tape and confirm that they all converge to a single point in space and time, the year 1054. This turns the image from a snapshot into a movie, a dynamic confirmation of our theories about stellar evolution. The Crab Nebula, therefore, serves as a masterclass in cosmic interpretation. It teaches us that a single astronomical object is not a simple picture but a complex dataset that can be read at different wavelengths, each revealing a different chapter of its history. It demonstrates the direct link between a historical event witnessed by our ancestors and the advanced astrophysical processes we study today. From the violent death of a star to the birth of a pulsar and the scattering of life-giving elements, the entire life cycle is encoded in the light we receive. By learning to decode this light, we learn to read the universe itself, transforming a beautiful wisp in the night sky into a profound testament to the interconnectedness of cosmic birth, death, and renewal. There is a profound and enduring puzzle that lies at the intersection of science and human perception, one that has intrigued philosophers and physicists for centuries. Why is it that the universe, governed by mathematical laws we can barely comprehend, so often presents itself to us in forms of breathtaking beauty, the elegant spiral of a galaxy, the intricate lacework of a nebula's gas clouds, the perfect, serene geometry of Saturn's rings? These are not just scientifically informative, they are aesthetically magnificent. This correlation feels too strong to be mere chance. It suggests a deep and mysterious connection between the principles that shape reality and the faculties through which we appreciate it. We are drawn to these images not only as scientists seeking data, but as human beings seeking wonder, and this dual attraction may be the most important clue we have. This allure of beauty is not a superficial preference. It is rooted in cognitive principles that have guided human understanding for millennia. Our brains are pattern recognition engines, exquisitely tuned to find order in chaos. We are instinctively drawn to symmetry because in the natural world, symmetry often signifies health, stability, and efficiency. A symmetrical face is perceived as healthy. A symmetrical snowflake forms under perfect physical conditions. In the cosmos, this principle scales up magnificently. The rotational symmetry of a spiral galaxy is a direct consequence of the conservation of angular momentum, a fundamental law of physics. The beautiful, balanced structure is a visual signature of an efficient, stable system. Similarly, we find complexity compelling, but only when it is structured complexity. The chaotic beauty of a supernova remnant with its filaments and shockwaves is not random noise. It is a complex pattern born from a simple, explosive event interacting with its environment, a story of cause and effect written in light and gas. The beauty we perceive is our mind's way of recognizing an underlying, elegant order. This idea elevates aesthetics from a passive experience to an active tool for discovery. Throughout the history of science, the concept of beauty has often served as a heuristic, a practical guide that points researchers toward promising theories. When a physicist is confronted with several competing equations to describe a phenomenon, there is a long-standing tradition of choosing the one that is more elegant, more symmetrical, the one that feels mathematically beautiful. This is not mere scientific vanity. Time and again, this instinct has proven correct. The fundamental equations of general relativity and quantum mechanics are celebrated for their mathematical beauty, their profound simplicity that gives rise to an infinite tapestry of complex outcomes. The universe seems to operate on principles that are, at their core, elegant. Therefore, when we see a visually beautiful structure in space, we are likely seeing a manifestation of that underlying physical elegance. Our innate sense of beauty becomes a compass, pointing our curiosity toward the most fundamental and universal truths. The stunning image is a gateway, inviting us to uncover the simple, powerful law that created it. This leads to a truly humbling possibility. The fact that we can not only decipher the universe's laws, but also find them beautiful suggests a strange consonance between our minds and the cosmos. The mathematician and physicist Eugene Wigner famously called this the unreasonable effectiveness of mathematics in the natural sciences. Why should the human mind, a product of evolution on a tiny planet, be capable of formulating abstract mathematics that so perfectly describes the behavior of a quasar or the curvature of spacetime. The fact that we can look upon the pillars of creation and feel awe, while simultaneously understanding the physics of their evaporation, is a profound duality. It suggests that our sense of beauty and our capacity for logic are not separate pursuits but intertwined strands of the same quest for understanding. We are not merely external observers of a cold, mechanical universe. We are products of it, and our consciousness seems uniquely tuned to appreciate its deepest harmonies. Ultimately, the greatest mystery revealed by the visual poetry of space may not be about the nature of dark matter or the origin of the Big Bang. It may be about the nature of knowledge itself. The universe is not only knowable, but it is also deeply, stirringly beautiful. This is a fact that transcends science and touches on philosophy. Does the beauty exist independently, or is it created in the interaction between the cosmos and the observer? The answer is likely both. The physical laws create the structures, and our perception finds the beauty within them. This partnership between the external universe and our internal experience is what transforms data into meaning. The aesthetics of cosmic mystery, therefore, are not a sideshow to the main event of science. They are an integral part of the revelation, a constant reminder that in our search for truth, wonder is not a distraction, it is our most reliable guide. But what if you could do more than just look at these cosmic wonders? What if you could step inside them to feel the immense scale of a galaxy with your own sense of space, or to stand on the dusty plains of an alien world and look up at its strange sky? This is no longer the realm of science fiction. We are now entering the era of interactive cosmic exploration, where virtual and augmented reality technologies are turning the universe from a distant spectacle into a personal, navigable domain. This represents the most profound evolution yet in our visual conversation with the cosmos, shifting us from being passive observers to active explorers. The fundamental power of this technology lies in its ability to translate abstract scale into intuitive, embodied understanding. We can look at a photograph of Jupiter and be told that the Great Red Spot is larger than Earth, but that fact remains an intellectual abstraction. Now, imagine putting on a VR headset and finding yourself floating in space near the giant planet. The sense of scale is immediate and visceral. You can turn your head and see the curve of its massive bulk stretching away to either side, a swirling tapestry of storms larger than continents. You can reach out with a virtual hand and watch as our own planet, a tiny blue marble, drifts past next to the colossal storm. This is not just learning, it is experiencing. The technology takes the vast, incomprehensible distances and sizes of space and makes them feel real in a way that a textbook or a screen simply cannot. It bridges the gap between the numbers we read and the reality they represent, grounding cosmic grandeur in the language of our own physical perception. This immersive experience is built upon a foundation of real, rigorous scientific data. These are not artistic fantasies, they are precise visualizations. Platforms like the video game, Elite Dangerous, or educational software like Space Engine use actual star catalogs, planetary survey data, and astrophysical models to construct their universes. When you fly to the TRAPPIST-1 star system, you are exploring a digital replica built from the known masses, orbital periods, and estimated compositions of its planets. When you stand on the surface of Mars in a VR experience created from NASA rover data, you are walking on a terrain mapped by the lasers and cameras of the Curiosity and Perseverance rovers. Every boulder, every crater, every slope is where it is because the data says it should be. This fusion of accurate data with immersive technology transforms these experiences from simple games into powerful tools for discovery. A scientist can literally step inside a simulation of a galaxy collision, watching millions of stars interact according to the laws of gravity, potentially spotting patterns or anomalies that might be missed on a two-dimensional graph. The implications for education are staggering. For a student learning about the solar system, the difference between reading about the moon's phases and virtually standing on its surface, watching the Earth go through its own cycles of light and dark, is the difference between memorization and genuine insight. Field trips are no longer limited by geography or budget. A classroom can now take a journey to the icy geysers of Saturn's moon Enceladus, or fly through the magnificent rings, watching sunlight glint off countless icy fragments. This active, exploratory learning fosters a deeper, more personal connection to the material. It makes the cosmos a place that can be visited and explored, not just a collection of facts to be learned. The wonder that was once reserved for astronauts is now accessible to anyone with the right equipment, democratizing the experience of cosmic awe and inspiring the next generation of scientists, engineers, and dreamers. Perhaps the most exciting potential lies in the future of scientific research itself. Astronomers often work with incredibly complex three-dimensional structures, from the distribution of dark matter in a galaxy cluster to the intricate topology of the cosmic web. Visualizing these structures on a flat screen forces a compression of information, but in a virtual reality environment, a researcher can be completely surrounded by the data. They can walk through a point cloud representing thousands of distant galaxies, seeing their spatial relationships from every angle. They can reach out and manipulate a simulation of a forming planetary system, slowing it down or speeding it up to observe dynamic processes. This embodied data analysis can lead to intuitive leaps and discoveries that might be elusive when working with traditional tools. It allows for a form of scientific intuition that is closer to that of a naturalist walking through a forest, observing patterns and interactions in a natural, three-dimensional context. This technology is the ultimate expression of the visual poetry we have been tracing. It takes the light captured by our telescopes, the data passed by our computers, and the physical laws described by our equations, and weaves them into an experience that engages our entire sensory being. It is the difference between looking at a map of a mountain range and actually hiking through it. The map is informative, but the hike is transformative. Virtual and augmented reality are building the trails for us to hike the cosmos. They promise a future where exploring the universe is not just something we do with our eyes and our minds, but with our whole sense of presence, making the greatest mysteries of space not just something we see, but something we feel, a reality we can step into and begin to truly call our own. This simple, profound truth is the key that unlocks the deepest dimension of cosmic imagery. Light, for all its incredible speed, does not travel instantaneously. It moves at a finite, though staggering, pace, about 186,000 miles per second. This universal speed limit means that every time we observe a celestial object, we are not seeing it in its present moment. We are receiving a message from its past. The light that enters our eyes or our telescopes has been on a journey, and the duration of that journey is a direct measure of how far back in time we are looking. This turns every single astronomical observation into an act of time travel, and every image into a unique historical document. Consider the familiar face of our nearest large galactic neighbor, the Andromeda Galaxy. That soft, fuzzy patch visible on a clear, dark night is not a contemporary portrait. The photons that left its stars began their voyage 2.5 million years ago. When that light departed on Earth, the earliest ancestors of humanity were just beginning to walk upright on the African savanna. The entire tapestry of human civilization, The rise of agriculture, the building of cities, every recorded war and peace has unfolded during the time it took that light to finally reach us. The Andromeda galaxy we see is a fossil image, a relic from a prehistoric era. For all we know, a cataclysmic event may have already transformed Andromeda, but that information is still en route, traveling at the speed of light and not due to arrive for another 2.5 million years. We are quite literally watching the past unfold in the sky above us. This effect scales with distance in the most extraordinary way. The Hubble Space Telescope's ultra-deep field pushed this concept to its absolute limit. By staring at a seemingly empty patch of sky for days, it gathered photons so ancient they predate the Earth itself. The faintest, reddest smudges in that image are galaxies whose light has been traveling for over 13 billion years. We are seeing them not as majestic spirals, but as infant systems, mere toddlers in cosmic terms, caught in the act of formation when the universe was less than 1 billion years old. The ultra-deep field is not a single snapshot from one moment in history. It is a layered archaeological dig. Each galaxy in the frame is seen at a different point in its evolution, depending on its distance. The image is a chaotic family portrait containing newborns, adolescents, and adults all at once, a visual compression of billions of years of cosmic history into a single, profound frame. This transforms our telescopes into far more than just cameras. They are time machines of unparalleled power. A radio telescope capturing emissions from a distant quasar is tuning into a broadcast from an era when galaxies were young and violent. The James Webb Space Telescope, with its infrared eyes, is specifically designed to look even further back than Hubble, to peer into the so-called dark ages of the universe, a time before the first stars and galaxies had fully ignited. With each technological leap, we are not just building a better telescope, we are constructing a more powerful portal into the past, allowing us to witness earlier and earlier chapters of the universal story. This profound temporal dimension adds an incredible layer of meaning to the visual poetry of space. The beauty of a nebula or the grandeur of a galaxy cluster is no longer just a spatial experience, it is a temporal one. We are not just looking at an object far away, we are looking at an event long ago. To study the cosmos is to become a historian of the universe, sifting through a fossil record written in light instead of stone. The night sky is not a static mural but a dynamic, ever-changing historical archive. Every star, every galaxy is a clock hand pointing to a different moment in the deep past. When we look up, we are engaging in the ultimate form of archaeological exploration, unearthing the secrets of cosmic evolution by simply collecting the ancient light that has been streaming toward us since the dawn of time. From Galileo's hand-sketched lunar craters to the James Webb Space Telescope's deep-time vistas of infant galaxies, our journey through the visual poetry of space has been a testament to humanity's unyielding curiosity. We have witnessed how these images are far more than mere decoration. They are the primary language of discovery, a sophisticated code that translates raw data into profound understanding and deepens mystery into tangible knowledge. These breathtaking portraits bridge the immense chasm between our human-scale existence and the cosmic immensity, making the universe accessible not just to our intellect but to our very senses, allowing us to feel the scale of a nebula and the history of a galaxy cluster. The ongoing quest for clearer, deeper, and more comprehensive imagery is at its heart a quest for meaning. It is driven by an insatiable desire to understand our origins, to chart our place in the grand tapestry of existence, and to answer the most fundamental questions about where we came from and what else is out there. This exploration serves as a powerful reminder to always look up, to nurture a sense of wonder, and to never cease in our pursuit of the beauty and truth so eloquently written in the light of the stars. We would love to hear from you. What is the cosmic image that has most profoundly moved you? Share your favorite in the comments below, and if you have enjoyed this journey, subscribe to continue exploring the wonders of the universe with us.